Hello there, and welcome. Tonight I want to take you somewhere very special, somewhere that exists only in the gentle space between waking and sleeping, between what we know and what we can imagine. I want to take you to a universe that looks almost exactly like ours, but with one profound difference that changes everything we thought we understood about seeing and being seen. Before we begin this journey together, I'd like you to notice where you are right now, perhaps tucked into bed, maybe curled up on a couch, or settled into your favourite chair. Notice how the weight of your body presses gently into whatever is supporting you, how your breathing has perhaps already begun to slow just a little bit as you prepare for this cosmic journey we're about to share. I'm curious about where you're listening from tonight, what time zone cradles you as we speak these words into the darkness. Are you in a bustling city where the lights never quite go out, or perhaps somewhere quieter, where the stars might actually be visible through your window? Whatever corner of our small world you're resting in right now, you're part of a gentle community of night listeners, all of us scattered across different continents and time zones, yet connected by this shared moment of curiosity and calm. If you'd like to be part of this quiet gathering, consider leaving a comment about where you're listening from and what time it is there, and perhaps, if this journey resonates with you, you might like and subscribe to join us for future explorations into the peaceful mysteries of our universe. There's something beautiful about knowing that while you drift off to sleep in one part of the world, someone else might just be waking up to these same words, these same questions, creating a continuous chain of wonder that circles our planet, like the Terminator line between day and night. The question I want to explore with you tonight is one that sounds impossible at first, perhaps even absurd, but I promise you that if you give it just a moment of your imagination, it will open a door to a kind of wonder that feels both vast and intimate, both strange and somehow deeply familiar. It's a question that physicists have never seriously asked because it seems to violate everything we understand about the fundamental nature of matter and energy, and yet, in the asking of it, we might discover something profound about the universe we actually inhabit. What if dark matter was visible and normal matter invisible? What if everything you've ever seen, touched, known, and loved was suddenly as transparent as the clearest glass, while all the mysterious invisible substance that makes up most of our universe suddenly began to glow with a soft, patient light? I know it sounds like the beginning of a science fiction story, and in a way it is, but it's also an invitation to think differently about the cosmos we float through every single day without really seeing it, without really understanding just how much of it remains hidden from our eyes. Let me explain what I mean by normal matter and dark matter, and I'll do it slowly, gently, because there's no rush here, no test at the end, nothing you need to remember perfectly. Normal matter is everything you've ever encountered in your life. It's the atoms that make up your body, the air you're breathing right now, the device you're listening to this on, the walls around you, the ground beneath you, the food you ate for dinner, the water you drink, the clothes you wear. It's also the Earth itself, the moon that might be visible through your window, the sun that warmed your face earlier today, all the planets in our solar system, every star you've ever seen or will ever see, every galaxy that astronomers have photographed with their powerful telescopes. Normal matter is made of protons, neutrons, and electrons, arranged in different patterns to create all the wonderful diversity of substances and objects in our world. When light bounces off normal matter or passes through it, we see it, we experience it, we know it's there. This is the matter that makes up everything familiar, everything that feels real and solid and present in our lives. But here's where the universe becomes strange and humbling. Scientists have discovered, through careful observations and calculations that I'll share with you gently throughout our journey, that normal matter makes up only about 5% of everything that exists. 5%. Let that settle into your awareness for a moment. Everything you've ever known, every person you've ever loved, every place you've ever been, every star in every galaxy that we can see, all of it together amounts to just 5% of the universe. The rest, about 27% of it, is what we call dark matter, and it's called dark because it doesn't interact with light in any way we can detect. It doesn't emit light, it doesn't absorb light, it doesn't reflect light. Light passes right through it as if it weren't there at all, and yet we know it exists because we can see its gravitational effects on the normal matter around it. Dark matter is like an invisible scaffolding that holds galaxies together, that shapes the large-scale structure of the universe, that influences how everything moves and evolves across cosmic time. In our real universe, the one you're resting in right now, dark matter is completely invisible to us. We can't see it, we can't touch it, we can't detect it directly with any instrument we've ever built. Billions of dark matter particles might be passing through your body right now, right this very second, and you would never know it. They ghost through you, through the Earth, through everything, interacting only through gravity, that gentle, persistent force that shapes everything from falling raindrops to the orbits of galaxies. But tonight, in this space between waking and sleeping, I want to invite you to imagine a different universe, one where the rules are gently reversed. In this imagined cosmos, normal matter becomes perfectly transparent, invisible, undetectable to our transformed eyes, while dark matter begins to glow with a soft, ethereal light that reveals the hidden architecture of everything. This isn't a scientific hypothesis, and I want to be clear about that from the beginning. No physicist thinks this could actually happen, and there's no mechanism in our understanding of physics that would allow for such a reversal. But that's not the point of our journey tonight. Sometimes, to understand something deeply, we need to imagine it differently, to turn it inside out in our minds and see what patterns emerge. Sometimes the most profound understanding comes not from facts and equations, but from gentle speculation, from asking what if, and following that question wherever it wants to lead us. And tonight, that question wants to lead us into a universe of invisible cities and glowing cosmic webs, of transparent planets and luminous galactic halos, of a reality that's both strange and beautiful, both alien and somehow more truthful than what our normal eyes can see. As we prepare to explore this inverted universe together, I want you to know that there's no wrong way to experience this journey. You might find yourself drifting in and out of attention, catching some parts clearly while others blur into a pleasant background hum, and that's perfectly fine. In fact, it's ideal. This isn't a lecture that demands your focused concentration. It's more like a lullaby with scientific wonder woven through it, a bedtime story for curious adults who find comfort in contemplating the vast mysteries of existence. You might fall asleep before we're halfway through, and if you do, perhaps your dreams will be touched by images of glowing cosmic structures and invisible worlds. Or you might find yourself following along for the entire journey, your mind gently engaged but your body completely relaxed, floating in that delicious space between consciousness and sleep, where imagination feels more real than reality. The universe we're about to explore exists in that same liminal space, neither fully real nor completely imaginary, but something in between, something that helps us understand both the universe we actually inhabit and the limitations of our human perception. We're so accustomed to thinking that what we see is what's real, that visibility equals existence, that our eyes tell us the truth about the world. But even in our normal universe, this isn't true. We can't see radio waves or X-rays or infrared radiation without special instruments. We can't see the magnetic fields that surround our planet or the gravitational waves that ripple through space-time. We can't see dark matter, which makes up most of the matter in the universe, or dark energy, which makes up even more. Our eyes, wonderful as they are, show us only a tiny slice of what's actually there, like looking at a vast ocean through a keyhole and thinking we understand the sea. So perhaps it's not so strange after all to imagine eyes that see differently, eyes that are tuned to a different aspect of reality. Perhaps it's even necessary, this act of imagination, to help us truly grasp just how much of the universe remains hidden from us, how much we're missing with our normal way of seeing. And perhaps, just perhaps, in imagining a universe where dark matter glows and normal matter fades away, we might discover something true about the nature of existence itself, something about the relationship between the seen and the unseen, the known and the mysterious, the small, bright fraction we call home and the vast, dark majority that surrounds us. In the universe we're about to enter, you would look down at your hands and see right through them, as if they were made of the clearest crystal, as if they weren't there at all. The walls of your room would be transparent, offering no barrier to your transformed vision. You could see through the Earth itself, straight through its transparent core to the stars on the other side, except that the stars themselves would also be invisible, their normal matter faded to perfect clarity. But you wouldn't be seeing nothing. Oh no, far from it. Instead, you would see the dark matter that surrounds us, that flows through us, that shapes the cosmic environment we unknowingly inhabit. You would see it glowing with a soft, patient light, not bright like the sun or sharp like a laser, but gentle, diffuse, like moonlight through fog or the aurora borealis on a quiet polar night. This glowing dark matter wouldn't be uniform or boring. It would have structure, beautiful and complex structure that follows the laws of gravity but creates patterns we've never seen with our normal eyes. Around the Earth, even though the Earth itself would be invisible, you would see a subtle concentration of dark matter, a gentle brightening that follows the gravitational well our planet creates in space-time. It would be like seeing the invisible made visible through its effects, like watching wind made manifest not by the movement of leaves, but by the glowing of the air itself. The Moon's orbit would be traced by a faint river of light, and the Sun, our invisible Sun, would be surrounded by a vast halo of golden dark matter light, reaching out far beyond the orbits of the planets. As we prepare to journey deeper into this transformed cosmos, to explore what our solar system, our galaxy, our universe would look like through dark matter eyes, I want to remind you once more that this is a journey of imagination grounded in real science. Everything I'll share with you about dark matter, about its properties and behaviors, about how it clusters and flows, is based on actual observations and theories that scientists have developed over decades of careful work. We're simply taking that real science and asking a playful but profound question. What if we could see it? What if the invisible majority of the universe suddenly revealed itself to our wondering eyes? The implications of this thought experiment ripple outward in all directions, touching on physics, philosophy, human meaning, and our place in the cosmos. If dark matter were visible, how would human history have unfolded differently? What stories would we tell about the glowing structures in the night sky? How would we understand ourselves and our significance when we could see that we're made of the rare, exotic stuff, rather than the common, abundant matter that fills most of the universe? These are the kinds of questions we'll explore together, slowly, gently, with no urgency and no need for definitive answers. The questions themselves are lullabies, invitations to wonder that can carry us into peaceful sleep while keeping our minds gently engaged with the mysteries of existence. But I'm getting ahead of myself, carried away by the possibilities that unfold from this simple reversal of visible and invisible. Let's return to where you are right now, in your bed or chair, in your room with its familiar walls that you can see, surrounded by all the normal matter that makes up your life. Feel the weight of your body again, notice your breathing, notice how you've perhaps already begun to relax more deeply, just from listening to these words, from contemplating these ideas. This is exactly where you should be, exactly how you should feel. There's nowhere you need to go, nothing you need to do, no effort required beyond simply listening and imagining, or not even that if you prefer to just let the words wash over you like gentle waves on a distant shore. In a moment, we'll begin to transform your vision, to slowly adjust your imaginary eyes to see dark matter instead of normal matter. It will be a gradual process, like eyes adjusting to darkness, except instead of darkness, you'll be adjusting to a different kind of light, a light that's always been there but that you've never been able to see before. We'll start with your immediate surroundings and slowly expand outward, from your room to your city, from Earth to the solar system, from our local neighborhood to the vast cosmic web that connects all galaxies across billions of light-years of space. Each stage of this journey will reveal new wonders, new structures, new ways of understanding the universe we inhabit. But remember, there's no rush. We have hours ahead of us, hours to explore and wonder and drift. If you feel yourself getting sleepy, don't fight it. Let sleep come if it wants to. These ideas will still be here, patient and eternal as dark matter itself, waiting for whenever you want to return to them. And if you stay awake, floating in that delicious drowsy state, where imagination feels more vivid than everyday reality, that's perfect too. This journey is designed for that state, crafted to be engaging enough to hold your gentle attention, but soothing enough to guide you toward rest. The transformation is about to begin, and I want you to know that you're safe throughout this entire journey. We're not going anywhere dangerous or frightening. There are no cosmic catastrophes waiting for us, no threats to Earth or humanity, no alarming revelations that will disturb your peace. This is a journey of pure wonder, of gentle curiosity, of the kind of speculation that expands the mind while calming the body. We're going to see beautiful things, strange things, things that will make the universe feel both larger and more intimate than you might have imagined. But all of it will be presented with the same calm, measured tone, the same peaceful pacing, the same care for your comfort and rest. So let's begin this transformation together. Take a slow, deep breath, and as you exhale, imagine that your eyes are beginning to change, not physically, of course, but in their ability to perceive, in what they're tuned to detect. With each breath, normal matter becomes a little more transparent, a little less visible, while dark matter begins to show the faintest glimmer of light. It's subtle at first, so subtle you might not even notice it. The walls of your room seem perhaps a tiny bit less solid, a tiny bit more translucent, like looking through frosted glass that's slowly becoming clearer. Meanwhile, in the spaces between things, in what you thought was empty air, the faintest suggestions of light begin to appear, like the first stars emerging in the evening sky, so dim you're not sure if you're seeing them or imagining them. This is how our journey begins, with this gentle shift in perception, this slow tuning of imaginary senses to a different channel of reality. And already, even with this tiniest of changes, the universe is becoming stranger and more wonderful. Because that faint light you're beginning to see, that's not coming from atoms or molecules or any familiar form of matter. That's dark matter itself beginning to reveal its presence, beginning to show you the hidden architecture that's been surrounding you all along. It's been flowing through your room, through your body, through everything you've ever known, invisible and intangible, but absolutely real, shaping the cosmos on the larger scales while remaining completely hidden on the small scales of human life. As we continue this transformation in the next phase of our journey, as normal matter fades further and dark matter brightens, you'll discover that you're not losing the world you know, but gaining a new one, a parallel reality that exists in the same space, but reveals different truths. The familiar and the mysterious will blend together in ways that might surprise you, might comfort you, might lull you into the deepest and most peaceful sleep you've had in quite some time. Because there's something profoundly soothing about recognizing that we're surrounded by mysteries, that the universe is far stranger and more wonderful than our everyday experience suggests, that there are entire categories of existence we can't perceive, but that nevertheless cradle us, shape us, include us in their vast and patient patterns. The transformation that began so gently is now deepening, and with each breath you take, the familiar world you've known all your life is becoming something altogether different, altogether more mysterious. Your walls, those solid barriers that have always defined the boundaries of your personal space, are now translucent like sheets of the finest glass, and if you look carefully, you can see through them to whatever lies beyond. Perhaps it's another room, perhaps it's the outside world, but even those distinctions are beginning to blur because everything made of normal matter is taking on this same crystalline transparency. Your furniture, your belongings, the very floor beneath you, all of it is fading into a kind of architectural ghost, still present in some sense because you can feel it supporting you, but no longer visible to your transformed eyes. And what about your own body? If you look down at your hands now in this imagined universe we're exploring together, you would see right through them as if they were made of the purest water, as if they weren't there at all. You might still feel them, still move them, still use them to interact with the invisible normal matter around you, but visually they would have vanished, leaving only the faintest outline where they interact with the growing light of dark matter. It's a strange thought, isn't it, to imagine yourself as invisible, to think of your physical form as transparent. But don't let it disturb you. In this universe we're imagining, everyone would be equally invisible, all of us made of the same transparent normal matter, all of us seeing by the light of dark matter rather than the familiar photons we're used to. The air around you, which has always been invisible anyway, remains so, but now for a different reason. It's not that air is transparent to visible light anymore, it's that the nitrogen and oxygen molecules that make up air are composed of normal matter, and normal matter has become completely unseeable in our thought experiment. But the space that air occupies isn't empty, not truly empty. As your dark matter vision continues to sharpen, to attune itself to this different spectrum of existence, you begin to notice that what you thought was empty space is actually filled with a faint ethereal glow. It's not bright, not overwhelming, but it's there, a subtle luminescence that seems to come from everywhere and nowhere at once, like being inside a cloud that's lit from within by the softest possible light. This glow isn't uniform, and that's where things become truly fascinating. Dark matter, you see, doesn't spread out evenly through space like a perfect gas. It clusters, it flows, it responds to gravity just like normal matter does, but without all the complications of electromagnetic forces, without the pressure and collisions that normal matter experiences. Dark matter particles, whatever they actually are, and scientists still aren't sure about their true nature, pass right through each other, through normal matter, through everything except the fabric of space-time itself, which they bend and warp with their gravity just like any other form of mass does. So the dark matter around you, the dark matter you're now beginning to see, has structure, has patterns, has a kind of architecture all its own. Near the floor, or rather near where the floor would be if you could still see it, the dark matter glow is slightly brighter. Not much, just a subtle intensification of that ethereal light, but it's there, and it's there because the Earth beneath you, invisible though it now is, still has mass, still has gravity, and that gravity pulls dark matter toward it just as it pulls you toward it. The dark matter can't stop at the Earth's surface like you do, can't rest on the ground, because it doesn't interact with normal matter through any force except gravity. So it passes right through, sinking toward the Earth's center, creating a gentle concentration that peaks at the core and extends outward in all directions, far beyond the boundaries of our invisible planet. If you could see through your transparent walls, through all the transparent buildings and trees and everything else made of normal matter, and if you look toward where you know the ground should be, you would see this concentrated glow of dark matter extending downward, growing gradually brighter as it approaches the Earth's center. It's not a sharp boundary, not like the surface of the Earth in our normal vision, but rather a gradual intensification, like looking at a light through increasingly dense fog. The Earth, in dark matter vision, doesn't have a surface. It has a gravitational well that dark matter falls into and pulls within, creating a roughly spherical concentration of that gentle, patient light. But the dark matter doesn't stop at the Earth's center. It passes through, emerges on the other side, and spreads outward again, some of it escaping back into space, some of it falling back to make another pass through our invisible planet. It's a constant flow, a cosmic circulation that's been happening for billions of years and will continue for billions more. The dark matter particles, if that's what they are, move through the Earth like neutrinos do, like ghosts do in stories, except these ghosts glow with their own subtle light in our imagined universe, revealing their presence even as they refuse all other forms of interaction. As your dark matter eyes continue to adjust to become more sensitive to this different kind of light, you begin to notice more subtle patterns in the glow around you. There are streams and currents, rivers of slightly brighter dark matter flowing through the background glow like ocean currents through the sea. These streams aren't random, they follow specific paths, specific trajectories that are determined by the complex gravitational dance of everything in our solar system, our galaxy, our local group of galaxies. Some of these streams are ancient dark matter that's been flowing along the same paths for millions or billions of years. Others are newer, dark matter that's been recently captured by our galaxy's gravity, or perturbed by the passage of some massive object we never even knew was there. The streams move slowly by human standards, perhaps a few hundred kilometers per second, which sounds fast but is actually leisurely by cosmic standards. You can't see individual particles of dark matter, of course, any more than you can see individual photons of light. What you see is the collective glow of countless particles, quadrillions upon quadrillions of them, each following its own path through space-time but together creating these visible patterns, these rivers of light flowing through the darkness. Some streams are moving toward the constellation of Cygnus, where our solar system is heading in its orbit around the galaxy. Others come from the opposite direction, dark matter that our solar system is ploughing through like a ship through cosmic seas. And there's a wind, a dark matter wind that blows through everything, through you, through the Earth, through the entire solar system. This wind is created by our motion through the galaxy, by the fact that we're not stationary, but moving at about 220 kilometers per second, in our orbit around the galactic centre. The dark matter doesn't orbit with us, or at least not all of it does. Much of it forms a vast, roughly stationary halo around the galaxy, and we're flying through it, creating this apparent wind in our reference frame. In your transformed vision, this wind might appear as a subtle directional bias to the glow, slightly brighter in the direction we're moving, slightly dimmer behind us, like looking at snow being blown past a streetlight on a winter night. The temperature outside, the weather, the time of day, none of these familiar variations affect the dark matter glow. It shines with the same patient light whether it's noon or midnight, summer or winter, clear or stormy. The normal matter phenomena that create weather, that block or scatter sunlight, that make our days and nights, are all invisible now, unable to interact with the dark matter light that fills your transformed vision. This is a light that transcends human timescales, human weather, human concerns. It's been glowing like this since long before Earth existed, and will continue long after the sun has died and taken all the inner planets with it. But don't let that vast timescale make you feel insignificant. You're seeing something magnificent here, something that no human eyes have ever actually seen, but that physics tells us must be there. You're seeing the invisible scaffolding of the universe, the dark skeleton that holds everything together, that prevents galaxies from flying apart, that creates the large-scale structure of the cosmos. And you're seeing it from inside, from within the gravitational well of a small planet orbiting an ordinary star in an unremarkable part of a typical galaxy. You're seeing it from the perspective of the rare, exotic, normal matter, the small 5% that nevertheless managed to create stars and planets and life and consciousness, and the ability to wonder about the other 95%. As you lie there in your invisible bed, in your transparent room, surrounded by the gentle glow of dark matter, you might wonder what else you could see if you looked beyond your immediate surroundings. What does your neighbourhood look like in dark matter light? Your city? The entire planet? These are questions we'll explore as we continue our journey, as we expand our view from the personal to the planetary to the cosmic. But for now, just rest in this new way of seeing, this gentle glow that surrounds you, that passes through you, that connects you to structures and patterns far larger than anything human civilization has ever built. The dark matter light isn't harsh or glaring. It doesn't hurt your transformed eyes or make you squint. It's the softest light imaginable, like the phosphorescence of deep-sea creatures or the glow of certain mushrooms in a dark forest, but even gentler, even more diffuse. It's a light you could stare at forever without strain, a light that seems designed for contemplation rather than action, for wonder rather than work. In the imagined universe we're exploring, this would be the only light available for seeing, the only illumination by which to navigate reality. The sun's normal light would be invisible, the star's light unseeable, all the electromagnetic radiation that floods our normal universe would pass by undetected. Only gravity would reveal itself through the gentle glow of dark matter, and gravity, as Einstein taught us, is really just the curvature of space-time itself. Think about what this means for a moment. In our thought experiment, you're not really seeing matter at all, not even dark matter in the conventional sense. You're seeing the shape of space-time itself, the invisible geometry that governs how everything moves, how everything falls, how everything orbits and clusters and flows. The dark matter glow is like a tracer die in the cosmic ocean, revealing currents and depths that would otherwise be completely hidden. It's showing you the true shape of reality, or at least one aspect of it that our normal eyes can never perceive, and what a shape it is. Even here in your room in this small local volume of space, the patterns are complex beyond easy description. There are the large-scale flows I mentioned, the streams and winds created by our motion through the galaxy. But there are also smaller eddies and vortices, places where dark matter swirls and pools due to local gravitational influences. The moon, invisible though it is in our transformed vision, creates its own subtle disturbance in the dark matter field, a moving concentration that orbits the Earth every month, raising dark matter tides just as it raises ocean tides on our invisible planet. The sun's influence is even stronger, creating a vast region of enhanced dark matter glow that extends far beyond the orbit of Neptune. This is the sun's gravitational sphere of influence, the region where its gravity dominates over the background galactic field. In our normal universe, We define the solar system by the planets and asteroids and comets that orbit the Sun, all made of normal matter, all invisible in our thought experiment. But in dark matter vision, the solar system would be defined by this glowing cocoon, this roughly spherical region of enhanced light that marks the Sun's gravitational domain. Within that cocoon, each planet creates its own smaller sphere of influence, its own local brightening of the dark matter glow. Jupiter, the largest planet, would have the most pronounced effect after the Sun, creating a moving bright spot that completes an orbit every 12 years. Saturn, Uranus and Neptune would create their own mobile concentrations, and even little Mercury, racing around the Sun every 88 days, would leave a faint but detectable trace in the dark matter light. The planets themselves would be invisible, but their gravity would be revealed, their presence made known through the patient, persistent glow of dark matter falling into their gravitational wells. It's a different kind of beauty than what we're used to, isn't it? Not the sharp, bright beauty of stars against a dark sky, not the colourful beauty of sunsets and auroras, but something more subtle, more fundamental. It's the beauty of pure structure, of the cosmic architecture itself made visible. It's like seeing the wind by watching smoke, or seeing magnetic fields by watching iron filings, or seeing music by watching cymatics patterns in sand. The dark matter glow reveals forces and structures that are always there but always hidden, always shaping our reality but never directly showing themselves to our normal senses. As you continue to observe this gentle light, you might notice that it has a quality unlike any normal light you've experienced. Normal light travels in straight lines, or at least it does in a vacuum, creating sharp shadows and clear boundaries between illuminated and dark areas. But dark matter light in our imagination doesn't work that way. It doesn't cast shadows because it doesn't travel in rays from specific sources. Instead, it simply glows wherever dark matter is present, which is everywhere, just more intensely in some places than others. There are no dark matter shadows, no places where something blocks the dark matter light, because nothing can block dark matter. It passes through everything, normal matter, and other dark matter alike, interacting only through gravity, revealing only the shape of space-time itself. This shadowless light creates a strange visual effect. Everything appears to be lit from within, self-luminous, glowing with its own patient radiance. There's no sense of direction to the light, no way to tell where it's coming from because it's coming from everywhere. It's omnipresent, omnidirectional, a field of light rather than beams of light. In some ways it might be like being inside a giant fluorescent bulb, where the light seems to come from the entire volume of space rather than from specific points. But even that analogy doesn't quite capture it because fluorescent light is still electromagnetic radiation, still photons, still part of the normal matter universe that we've made invisible in our thought experiment. The colour of dark matter light is another interesting question. What colour would it be? In reality, dark matter doesn't emit any electromagnetic radiation, so it has no colour in the conventional sense. But in our imagined universe, where we've given it the property of visibility, we might imagine it as a deep, rich gold, like honey held up to candlelight, or perhaps a soft silver blue, like moonlight on water. Or maybe it would be a colour we've never seen before, a colour that doesn't exist in our normal electromagnetic spectrum, something beyond violet or below red, a colour that only dark matter eyes could perceive. For tonight, for this journey, let's imagine it as a warm, golden glow, comforting and ancient, like the light of a hearth fire that's been burning since the beginning of time. This golden light fills everything, permeates everything, connects everything. It makes the entire universe into a single, glowing whole, with variations in brightness, but no true darkness anywhere. Even in what we would normally call the emptiest regions of intergalactic space, there would still be a faint dark matter glow, dimmer than anywhere else but never completely absent. The universe in dark matter light would never be truly dark, never completely black. There would always be that patient, persistent glow, that evidence of the invisible majority that shapes everything we see, or in this case, everything we can't see. Let's bring this cosmic vision down to Earth now, down to the familiar spaces and places you know so well, but transformed by our imaginary dark matter sight into something altogether more mysterious. Imagine stepping outside your transparent home into a world where every building, every tree, every car and street and sidewalk has become as clear as air, invisible to your transformed eyes. The city around you, if you live in a city, or the town, or the countryside, whatever familiar landscape you call home, all of it has vanished visually, leaving only the golden glow of dark matter to guide your way. You can still feel the ground beneath your feet, of course, still bump into invisible walls if you're not careful, still interact with all the normal matter that makes up our world, but you can't see any of it. Instead, you see the dark matter architecture that surrounds and permeates everything, the usually hidden structure that coexists with our familiar world. The first thing you might notice is that the dark matter glow isn't uniform across the landscape. Where there are invisible hills and mountains, the glow intensifies slightly, following the concentration of mass. Where there are valleys and depressions, the glow dims just a bit, reflecting the lesser gravitational pull. It's as if you're seeing a topographical map made of light, where elevation is indicated not by contour lines but by variations in luminosity. The invisible mountains glow like gentle beacons, not bright enough to hurt your eyes, but definitely brighter than the surrounding plains. The valleys are dimmer, though never truly dark, like looking at a landscape through amber-tinted glass where some areas are thicker than others. If you live near the ocean or any large body of water, you would notice something particularly interesting. The water itself is invisible, of course, being made of normal matter, but its gravitational effect on dark matter creates a distinct pattern in the glow. The ocean basins, those vast depressions in the Earth's crust filled with invisible water, appear as regions of slightly dimmer light, while the invisible continents glow a bit brighter due to their greater density. It's like looking at a photographic negative of the Earth's surface, where the familiar patterns of land and sea are revealed not by their appearance but by their gravitational signatures written in dark matter light. Walking through your invisible city would be a surreal experience. The streets themselves would be unmarked, except by the subtle gravitational patterns they create. The slight depression where the road has been carved through higher ground. The gentle rise where it climbs an invisible hill. But the buildings, those massive concentrations of concrete and steel and glass, they would reveal themselves through the dark matter glow. Each skyscraper would be surrounded by a subtle halo of enhanced light, the dark matter responding to the gravitational pull of all that concentrated mass. The taller the building, the more pronounced the effect, creating vertical columns of slightly brighter glow reaching up into the sky. You could walk right through the walls of these buildings, at least visually, seeing through floor after floor as if they weren't there. But you'd see the gravitational architecture they create, the way dark matter pools more densely in their invisible foundations, the way it flows around their mass like water around rocks in a stream. In the business districts where the buildings are tallest and most densely packed, the dark matter glow would be noticeably brighter, a golden radiance marking the gravitational centre of the city. In the suburbs where the buildings are smaller and more spread out, the glow would be dimmer, more uniform, a gentle background luminescence without much variation. Parks and green spaces, which we normally think of as empty areas within cities, would appear almost the same in dark matter light as the built-up areas around them. The trees are invisible, the grass is invisible, the ponds and paths are all invisible. Only if the park sits in a depression or on a hill would you notice any difference in the dark matter glow. This is one of the strange aspects of our thought experiment. The living world, the biological world that seems so important to us, would be almost completely erased from view. All that complex organization of matter into cells and tissues and organisms would be invisible, leaving only the raw gravitational signature of mass, regardless of how that mass is organized. But let's think more carefully about how you would navigate this invisible world. You're walking down what you know to be a street, though you can't see it. Other invisible people are presumably walking past you, though you can't see them either. Cars made of normal matter are driving by, invisible and silent to your dark matter senses, because sound is carried by normal matter air molecules that you can no longer perceive. It would be a world of ghostly presences, where you know things are there but can't directly observe them. You would have to navigate by memory, by touch, by the subtle gravitational patterns in the dark matter glow, and by faith that the familiar world still exists even though you can no longer see it. The weather would be completely imperceptible in this dark matter vision. Rain, snow, fog, clouds, all of these are made of normal matter, and would be invisible. A thunderstorm could rage around you, and you wouldn't see the lightning or the rain, though you might notice very subtle changes in the dark matter glow as the mass of water moves through the atmosphere. The wind wouldn't be visible either, though the dark matter wind I mentioned earlier, that cosmic flow created by our motion through the galaxy, that would still be there, a gentle directional bias to the omnipresent glow. Day and night would lose their familiar meaning. The sun, being made of normal matter, would be invisible, its light unseeable. The blue sky, the clouds, the stars, all gone from view. Instead, there would be the constant, patient glow of dark matter, unchanging whether it's noon or midnight. The only variation would come from the moon's invisible orbit, creating a subtle monthly cycle in the local dark matter density, and from the Earth's orbit around the sun, creating a yearly cycle as we move closer to and farther from the sun's dark matter concentration. But these changes would be so subtle, so gradual, that you probably wouldn't notice them without careful observation over long periods. Temperature would be another strange aspect of this dark matter world. Dark matter doesn't interact electromagnetically, which means it doesn't absorb or emit heat in the way normal matter does. It wouldn't feel hot or cold to the touch because you couldn't touch it at all. It would pass right through you without any sensation except the visual glow we've imagined for it. So even as the invisible normal matter world goes through its daily and seasonal temperature cycles, the dark matter glow would remain constant, unaffected by the heat of summer or the cold of winter. It would be a kind of eternal cosmic room temperature, neither warming nor cooling, just persistently, patiently glowing. Imagine standing at the edge of your invisible city, looking out toward the countryside beyond. Without buildings to create gravitational concentrations, the dark matter glow would smooth out, becoming more uniform, like looking at a calm sea of golden light extending to the horizon. Mountains in the distance would appear as glowing peaks, brighter than the surrounding plains, but softer and more diffuse than mountains appear in normal vision. There would be no sharp edges, no clear boundaries, just gradual transitions from brighter to dimmer and back again. Rivers and lakes would be particularly interesting in this dark matter vision. The water itself would be invisible, but the depression it fills would affect the dark matter distribution. A river valley would appear as a slightly dimmer channel winding through the landscape, while the invisible water flowing through it would create subtle, moving variations in the glow. Lakes would be like holes in the dark matter light, not completely dark, but noticeably dimmer than the surrounding land. The Great Lakes, if you were near them, would appear as vast dim regions, like looking at the night sky through patches of thin cloud. Underground, the situation would be even stranger. In our normal vision, going underground means entering darkness unless we bring artificial light. But in dark matter vision, the underground would glow just as much as the surface. Perhaps even more so because you'd be surrounded by the mass of the Earth on all sides. Mining tunnels, subway systems, basements, all of these would be navigable by dark matter light, though you still couldn't see the walls or floors or ceilings that contain them. You could walk through an invisible subway tunnel, following the gentle glow of dark matter, trusting that the invisible train won't hit you because you can't see or hear it coming. The ocean would present its own unique characteristics in this dark matter vision. The surface of the ocean, that boundary between air and water that we're so familiar with, would be completely invisible. You could walk from the beach into the water without seeing any change except for a very subtle dimming of the dark matter glow as you move from the denser continental crust to the less dense water. Underwater, if you could somehow survive there without seeing the water or any of the normal matter equipment that would keep you alive, the dark matter glow would continue, perhaps slightly dimmer than on land, but still present, still providing that golden illumination. The ocean floor would create its own patterns in the dark matter light. Underwater mountain ranges, the mid-ocean ridges where new seafloor is created, would glow brighter than the abyssal plains. Deep ocean trenches, those places where the seafloor plunges to its greatest depths, would appear as dim valleys in the dark matter light. The entire structure of the ocean floor, usually hidden beneath miles of opaque water, would be revealed in a soft three-dimensional map of gravitational variations. But perhaps the most profound aspect of walking through this dark matter world would be the emotional and psychological effect of seeing through everything, of having no visual barriers, No privacy, no hidden spaces. Every building is transparent, every wall is invisible, every person is unseeable. You could look straight through the Earth itself if the dark matter glow wasn't in the way, see through to the other side of the planet where people in China or Australia are going about their invisible lives. It would be a world without visual secrets, without the comfort of enclosed spaces, without the familiar boundaries that define our personal and social spaces. Yet at the same time, it would be a world of ultimate privacy, because no one could see you either. You would be invisible to everyone else, just as they are invisible to you. Only the dark matter glow would be shared, that cosmic light that belongs to no one and everyone simultaneously. It's a paradox, total transparency leading to total privacy, complete openness resulting in complete isolation, at least visually. You would have to rely on other senses, on touch and proprioception, on memory and imagination, to maintain your connection to the world and to other people. Think about what this would mean for human society, for how we would organize ourselves if this were actually our reality, rather than just a thought experiment. Architecture would be meaningless in the traditional sense because buildings wouldn't provide visual shelter or privacy. Art, at least visual art, would be impossible, because there would be nothing to see except variations in dark matter glow. Writing wouldn't exist because ink and paper would be invisible. We would have to develop entirely different ways of communicating, of creating, of expressing ourselves. But let's not get too far ahead of ourselves. We're still just walking through this invisible world, exploring what it would be like to navigate by dark matter light alone. Notice how your familiar neighborhood would be transformed, how the places you know so well would become alien and strange. That coffee shop you visit every morning, invisible, though its gravitational signature might create a tiny brightening in the dark matter glow. The park where you walk your dog, unseeable except for the gentle topography revealed by variations in the light. Your workplace, your gym, your favorite restaurant. All of them erased from view, leaving only the subtle gravitational architecture behind. And yet, even in this strange, invisible world, there would be beauty. The dark matter glow itself would be beautiful in its constancy, its patience, its gentle revelation of the universe's hidden structure. The patterns it creates, following the distribution of invisible mass, would have their own aesthetic appeal, like abstract art painted in light and gravity. The way it flows and pools and streams through space would be mesmerizing to watch, a kind of cosmic lava lamp that operates on scales from the personal to the universal. As you stand in this transformed world, surrounded by the golden glow of dark matter, you might feel a sense of peace despite the strangeness. There's something calming about this light that never changes, that doesn't flicker or flash or suddenly go dark. It's always there, always the same, a constant companion in what would otherwise be a visually empty universe. It connects you to everything else, reminds you that you're part of a larger structure, a cosmic web that extends far beyond Earth, far beyond our solar system, all the way to the edge of the observable universe. The human settlements scattered across our invisible planet would create their own patterns in this dark matter light. Cities would glow brighter than countryside, not because of streetlights or neon signs, which would all be invisible, but because of the concentrated mass of buildings and infrastructure. You could see the pattern of human civilization written in gravitational light, the networks of cities connected by dimmer rural areas, the bright spots where millions of invisible people have gathered together, the dimmer regions where few people live. From a high vantage point, if you could somehow get there without seeing the mountain or building or aircraft you're standing on, you could look out across the landscape and see these patterns spreading across the invisible Earth. The great metropolitan areas would be golden beacons, while the farmland and forest between them would be dimmer seas of gentler light. Rivers would be dark threads winding through it all, and mountain ranges would be glowing barriers dividing one region from another. It would be a map made of light, a gravitational cartography that reveals the structure of our world in a completely different way than we're used to seeing it. But this map would be missing so much that we normally consider important. National borders would be invisible because they're just human constructs with no gravitational signature. Roads would be unseeable except where they cut through hills or fill valleys. The difference between forest and farmland, between desert and grassland, between urban park and urban development, All of these distinctions that seem so important to us would be erased, leaving only the raw distribution of mass and the dark matter glow that follows it. Walking through this world, you would have to develop new ways of orienting yourself, new landmarks based on gravitational rather than visual features. That hill that glows a bit brighter than its surroundings, that valley that's a bit dimmer, that place where the city's gravitational field creates a distinctive pattern in the dark matter light. These would become your navigation aids. You would learn to read the subtle variations in the glow, to recognize places by their gravitational signatures rather than their visual appearance. And what about the night sky in this dark matter vision? Looking up, you wouldn't see stars or the moon or planets. The entire celestial sphere that has guided humanity for millennia would be invisible. Instead, you would see the dark matter structure of our local cosmic neighborhood. The plane of the Milky Way would be a band of brighter glow across the sky, not from stars but from the dark matter concentrated in our galaxy's disk and halo. Other galaxies, if they were close enough and massive enough, might appear as faint glowing smudges, their dark matter halos visible even though their stars are not. The moon's position would be marked by a concentration of dark matter moving across the sky, completing its monthly orbit around our invisible Earth. The sun's dark matter concentration would be obvious during the day, a bright region that moves across the sky, though its normal light and heat would be imperceptible. The planets would be too small and distant to create visible dark matter concentrations, lost in the general glow of the solar system's dark matter halo. It would be a sky without constellations, without the familiar patterns that humans have used for navigation and storytelling since prehistoric times. Instead, there would be new patterns, dark matter patterns, that reveal the gravitational structure of our cosmic neighborhood. These patterns would be much subtler than star patterns, requiring careful observation to discern, but they would be there, constant and patient, waiting for dark matter eyes to read them. As we prepare to leave Earth behind and venture out into the solar system, take one last look at this transformed world around you. See how different it is from the world you know, yet how it occupies the exact same space, the exact same location in the universe. Both worlds are real in their own way. The normal matter world you're familiar with is real, and the dark matter world we're imagining is real too, in the sense that dark matter really does surround us, really does flow through us, really does create the gravitational structures we've been visualizing. The only difference is that in reality we can't see the dark matter world. It remains invisible, intangible, known only through its gravitational effects on the normal matter we can observe. But by imagining it as visible, by giving it light and presence in our mind's eye, we can better appreciate the strange duality of our universe, the way two different kinds of matter coexist in the same space without ever truly touching, one visible but rare, the other invisible but common, together creating the cosmos we inhabit. Now let us lift gently away from Earth, rising slowly through the invisible atmosphere that we can no longer see, ascending through transparent clouds that don't obscure our vision because they simply aren't there to our dark matter eyes. As we float upward, the golden glow of Earth's dark matter concentration begins to spread out below us, no longer the sharp sphere we're used to seeing in photographs from space, but rather a gentle brightening that fades gradually into the background glow of interplanetary space. There's no sudden transition, no clear boundary where Earth ends and space begins, just a slow dimming of the light as we move away from the gravitational well our invisible planet creates in the fabric of space-time. The sensation of leaving Earth in this dark matter vision would be profoundly different from what astronauts experience. They see the blue marble of our world shrinking below them, the thin line of atmosphere giving way to the black of space, the stars emerging in their full glory without atmospheric interference. But in our imagined universe, none of that would be visible. Instead, you would experience a gradual transition from the relatively bright glow near Earth's surface to the dimmer but still present glow of the solar system's dark matter halo. It would be like ascending through layers of increasingly thin golden mist, each layer a bit dimmer than the one below, but never reaching true darkness. As we continue to rise, perhaps a few hundred kilometers above the surface, we begin to see the larger pattern of Earth's dark matter envelope. It's not a perfect sphere, this envelope, but slightly flattened at the poles due to Earth's rotation and slightly elongated in the direction of the Moon due to tidal effects. These distortions are subtle, barely perceptible, but they're there. revealing the dynamic gravitational environment our planet exists within. The dark matter doesn't just sit statically around Earth, it flows and shifts in response to all the gravitational influences acting upon it, creating a constantly changing but slowly evolving pattern of light. The Moon comes into view now, or rather, the Moon's dark matter signature becomes visible as a separate concentration distinct from Earth's. It appears as a moving bright spot, roughly spherical but much smaller and dimmer than Earth's glow, tracing its elliptical orbit through the darker background of cislunar space. The distance between Earth and Moon, that 250,000-mile gap that seems so vast to us, is bridged by streams of dark matter flowing between the two bodies, following the gravitational contours that connect them. It's as if Earth and Moon are connected by invisible threads of light, a luminous tether that has bound them together for billions of years. But the Moon's dark matter signature tells us something interesting about our satellite. Because the Moon is less massive than Earth, only about 1/80th of Earth's mass, its dark matter concentration is proportionally dimmer. But it's not just about mass, it's also about density. The Moon is less dense than Earth, lacking our planet's iron core, and this too affects how dark matter accumulates around it. The result is a gentler, more diffuse glow around the Moon, less concentrated than Earth's, but still clearly visible against the background. As we pull back further, rising to the distance of geostationary satellites, at about 36,000 kilometers, we can see the Earth-Moon system as a whole, a binary dance of light where the smaller partner orbits the larger, both of them surrounded by their overlapping dark matter halos. From this distance, we can also begin to see something else. The wake that the Earth-Moon system creates as it moves through the dark matter wind I mentioned earlier. Like a boat moving through water, our planet and its moon create a disturbance in the dark matter flow, a wake that streams out behind us in our orbit around the Sun. This wake isn't turbulent or chaotic. Dark matter doesn't behave like water or air. It doesn't create vortices or eddies in the same way. Instead, the wake is more like a gentle enhancement and diminishment of the background glow, brighter where dark matter has been compressed by our passage, dimmer where it's been rarefied. The pattern extends for millions of kilometers behind Earth, gradually fading back into the uniform background as the dark matter settles back into its undisturbed state. Now let's turn our attention sunward, toward the center of our solar system where our invisible star holds court. The Sun, even though we can't see its blazing surface or its corona or its solar wind, announces its presence through the most intense dark matter concentration in our solar neighborhood. As we approach it, the golden glow intensifies steadily, not sharply like approaching a light bulb in a dark room, but gradually, like walking toward a bonfire through thick fog. The Sun's gravitational well is so deep, its mass so great, that it creates a dark matter concentration that dominates the entire inner solar system. The Sun contains 99.86% of all the mass in our solar system, and this overwhelming gravitational presence is clearly visible in our dark matter vision. The glow around the Sun extends outward for millions of kilometers, gradually dimming with distance but never quite disappearing. It's like a vast golden atmosphere, but one that doesn't behave like a gas. It doesn't have pressure or temperature in the conventional sense. It simply exists, glowing with that patient light, revealing the shape of the Sun's gravitational field in 3 dimensions. Within this solar dark matter halo, the planets trace their ancient paths, each one creating its own moving concentration of light. Mercury, the innermost planet, races around the Sun every 88 days, its small mass creating only a modest brightening in the dark matter field. But because it's so close to the Sun, where the background dark matter glow is already intense, Mercury's contribution is hard to distinguish. It's like trying to see a candle flame in front of a bonfire. The light is there, but it's overwhelmed by the brighter background. Venus comes next, larger than Mercury and therefore creating a more pronounced dark matter signature. In our normal vision, Venus is the brightest planet in our sky, shining with reflected sunlight. But in dark matter vision, it's just another gravitational well, another concentration of invisible mass creating a moving bright spot in the solar halo. Its thick atmosphere, its crushing surface pressure, its runaway greenhouse effect, none of these dramatic features are visible. Only its mass matters, only its gravity speaks in the language of dark matter light. Earth we've already seen from the inside, but from out here in interplanetary space, Our home world is just another bright spot orbiting the Sun, distinguished only by being the third brightest planetary concentration after Jupiter and Saturn. Our blue oceans, white clouds, green and brown continents, all the features that make Earth so distinctive in normal light, are completely invisible. We're just another ball of matter creating a dimple in space-time, another place where dark matter gathers a bit more densely than in the surrounding void. Mars, the red planet that has captured human imagination for centuries, appears as a dimmer glow than Earth, befitting its smaller mass. Its two tiny moons, Phobos and Deimos, are far too small to create visible dark matter concentrations at this scale. They're lost in Mars's own glow, invisible even to our dark matter eyes. The great volcanoes of Mars, the vast canyon systems, the polar ice caps, all of these dramatic features that make Mars so interesting to planetary scientists are completely absent from our view. Only the total mass of the planet matters, creating a moving pool of light that takes 687 days to complete one orbit around the Sun. But now we come to something truly spectacular: the asteroid belt. In normal vision, the asteroid belt is mostly empty space with occasional rocks scattered through it, invisible unless you know exactly where to look with a powerful telescope. But in dark matter vision, the belt as a whole creates a subtle enhancement in the background glow, a ring of slightly brighter light between Mars and Jupiter. Individual asteroids are far too small to see, but collectively, their combined mass of about 3% of the Moon creates a detectable feature in the dark matter distribution. This ring isn't uniform. It's brighter in some places where asteroids cluster more densely, dimmer in others where they're more sparse. The largest asteroid, Ceres, which is actually classified as a dwarf planet, might be just barely visible as a tiny moving bright spot if we looked carefully enough. But mostly the asteroid belt appears as a gentle golden ring, like a cosmic halo marking the boundary between the inner and outer solar system. And then we reach Jupiter, the giant of our solar system, the planet whose mass exceeds all the other planets combined. In dark matter vision, Jupiter is magnificent, a moving beacon of golden light second only to the Sun itself in intensity. Its enormous mass, 318 times that of Earth, creates a dark matter concentration that extends far beyond the planet itself, encompassing its entire system of moons. The four large Galilean moons, Io, Europa, Ganymede and Callisto, create their own small bright spots orbiting within Jupiter's larger glow, like fireflies circling a lantern. Jupiter's dark matter halo interacts with the Sun's in complex ways, creating interference patterns where the two gravitational fields overlap. Streams of dark matter flow between them, following the invisible threads of gravitational force that connect all massive bodies. As Jupiter orbits the Sun every 12 years, it creates a moving disturbance in the solar dark matter halo, like a large ship creating waves in a harbour. These waves, these gravitational ripples in the dark matter distribution, propagate outward, affecting the entire solar system in subtle ways. Saturn comes next, almost as impressive as Jupiter in our dark matter vision. Its beautiful rings, so spectacular in normal light, are invisible here, being made of normal matter ice and rock. But Saturn's mass, 95 times that of Earth, creates a substantial dark matter concentration, and its large moon, Titan, adds its own noticeable glow to the system. The other moons of Saturn, dozens of them, create a constellation of tiny bright spots, most too small to see individually but collectively adding to the overall luminosity of the Saturnian system. The space between Jupiter and Saturn, and indeed between all the planets, isn't empty in our dark matter vision. It's filled with that omnipresent golden glow, dimmer than near the planets, but never completely dark. And through this glowing medium we can see streams and currents of dark matter, flowing along gravitational gradients, following paths determined by the combined gravitational influence of all the bodies in the solar system. Some of these streams are ancient, dark matter that's been orbiting the Sun for billions of years. Others are newer, dark matter recently captured from interstellar space or perturbed by the passage of the planets. Uranus and Neptune, the ice giants of the outer solar system, appear as dimmer glows in the distance, their lesser masses creating more modest concentrations of dark matter. Uranus, tilted on its side for reasons we still don't fully understand, creates a dark matter pattern that's slightly asymmetric, reflecting its unusual rotation. Neptune, the windiest planet in the solar system with speeds reaching 2,100 kilometers per hour, shows none of this meteorological violence in dark matter light. Its winds are invisible, its great dark spot unseeable. Only its mass speaks, creating a patient glow in the outer darkness. Beyond Neptune lies the Kuiper Belt, that vast region of icy bodies that includes Pluto and many other dwarf planets. In normal vision, the Kuiper Belt is almost impossible to see, its small dark objects reflecting very little sunlight. But in dark matter vision, like the asteroid belt, it creates a subtle enhancement in the background glow, a vast torus of slightly brighter light extending from Neptune's orbit out to perhaps 50 astronomical units from the Sun. It's much more diffuse than the asteroid belt, spread over a much larger volume, but it's there, marking the outer edge of the solar system's main disk. Pluto itself, demoted from planetary status but still beloved by many, creates a tiny moving bright spot, much dimmer than any of the 8 planets, but still detectable if you know where to look. Its large moon Charon creates its own even tinier glow, and the two orbit their common centre of mass every 6.4 days, a binary dance at the edge of the solar system. The other dwarf planets, Eris, Makemake, Haumea, and others yet to be discovered, each create their own small contributions to the dark matter glow of the outer solar system. But the solar system doesn't end at the Kuiper Belt. Far beyond, extending perhaps halfway to the nearest star, lies the Oort cloud, that hypothetical sphere of icy bodies that serves as the reservoir for long-period comets. We've never directly observed the Oort cloud. Its existence is inferred from the orbits of comets that seem to come from all directions, not just from the plane of the solar system. In dark matter vision, the Oort cloud might be visible as the faintest possible enhancement in the background glow, a barely perceptible sphere of light marking the true gravitational boundary of our Sun's influence. Within this vast sphere, comets move on incredibly elongated orbits, spending most of their time in the outer darkness, but occasionally falling toward the Sun in spectacular displays that we can't see in our dark matter vision. The comet itself, that dirty snowball of ice and rock, would be invisible, and its beautiful tail of gas and dust would be equally unseeable. But its mass, small as it is, would create a tiny moving point of light, racing inward toward the Sun, swinging around it in a tight curve, and then heading back out to the darkness from whence it came. The solar wind, that stream of charged particles that flows outward from the Sun at hundreds of kilometers per second, would be completely invisible in our dark matter vision. The heliopause, that boundary where the solar wind meets the interstellar medium, wouldn't appear at all. These are phenomena of normal matter, of electromagnetic forces, of the 5% of the universe we're used to dealing with. In dark matter vision, only gravity matters, only mass has a voice, and that voice speaks in the gentle language of golden light. Space missions would be strange affairs in this dark matter universe. Spacecraft, being made of normal matter, would be invisible, but their trajectories would be revealed by the paths they take through the dark matter glow. You could track a spacecraft's position by watching how it moves relative to the gravitational landmarks of planets and moons, but you couldn't see the spacecraft itself. Communication would be impossible through electromagnetic means, since radio waves are part of the normal matter universe. We would have to find some other way to send information, perhaps through gravitational waves, though those are far beyond our current technology to generate artificially. Think about the Voyager spacecraft, now heading into interstellar space after their grand tours of the outer planets. In our normal universe, we track them with radio signals, receiving their weak transmissions from billions of kilometers away. But in dark matter vision, they would be invisible points moving through the fading glow of the solar system's dark matter halo, heading out into the slightly dimmer glow of interstellar space. Their golden records, those messages to potential alien civilizations, would be invisible and unreadable. Only their tiny gravitational influence would mark their passage through the cosmos. The Parker Solar Probe, diving closer to the Sun than any previous spacecraft, would be invisible as it plunges through the intense dark matter glow near our star. Its heat shield, designed to withstand temperatures of nearly 1400 degrees Celsius, would be unnecessary in dark matter vision because dark matter doesn't carry heat. The probe would fly through the golden glow unharmed, at least by dark matter, though the invisible normal matter of the solar corona would still destroy it if it got too close. The James Webb Space Telescope, positioned at the second Lagrange point where the gravitational forces of Earth and Sun balance, would sit at a special place in the dark matter distribution. Lagrange points are gravitational features, places where the combined gravity of two bodies creates a stable or semi-stable position for a third, smaller body. In dark matter vision, these points might be visible as special patterns in the glow, places where the dark matter flow creates standing waves or stable vortices. They would be like cosmic parking spots, marked not by painted lines, but by the natural patterns of gravitational force. As we pull back even further, looking at the solar system as a whole from a distance of perhaps 100 astronomical units, we can see its overall structure in dark matter light. The Sun dominates the center with its intense golden glow. The planets orbit within this glow, each creating its own moving bright spot, with Jupiter and Saturn being their most prominent. The asteroid belt and Kuiper belt create subtle rings of enhanced light, and surrounding it all, extending far beyond the planets, is the vast, roughly spherical halo of dark matter that marks the Sun's gravitational domain. This halo isn't perfectly spherical, it's slightly flattened in the plane of the planets, where most of the solar system's angular momentum resides. It's also distorted by the gravitational influence of nearby stars, pulled and stretched by the galactic tide. And it's moving, the whole thing, travelling at about 220 kilometers per second in its orbit around the center of the Milky Way, creating that dark matter wind we experience on Earth. The boundary of the solar system in dark matter vision isn't sharp. There's no clear edge where our Sun's influence ends and interstellar space begins. Instead, there's a gradual transition, the golden glow slowly fading as we move outward, eventually merging with the background glow of the galaxy's dark matter halo. It's like walking away from a campfire on a misty night. You can't point to a specific place where the firelight ends, it just gradually fades into the darkness. But even in what we call interstellar space, the dark matter glow doesn't disappear entirely. The galaxy's dark matter halo extends far beyond the visible stars, creating a background glow that fills the spaces between star systems. This galactic dark matter forms streams and clouds, structures shaped by billions of years of gravitational evolution. Our solar system moves through these structures like a ship through cosmic seas, sometimes passing through denser regions where the glow brightens, sometimes through voids where it dims. Occasionally, our solar system might pass through a dark matter stream, a river of dark matter moving through the galaxy with its own velocity and direction. These streams are thought to be the remnants of smaller galaxies that were torn apart by the Milky Way's gravity, their dark matter stretched out into long filaments that orbit the galactic center. When we pass through such a stream, the local dark matter density increases, the glow brightens, and the dark matter wind shifts direction. These passages might last for millions of years, brief moments by cosmic standards, but far longer than human civilization has existed. There might also be dark matter subhalos, dense clumps of dark matter left over from the galaxy's formation, drifting through interstellar space like invisible clouds. If our solar system passed through one of these subhalos, the dark matter glow would intensify dramatically, perhaps becoming several times brighter than normal. The gravitational effects would be subtle but measurable, slightly perturbing the orbits of the planets and asteroids. But in our normal vision, we would see nothing unusual, just the familiar stars and empty space. The nearest stars to our Sun, Proxima Centauri and the Alpha Centauri system, would be visible in dark matter, light as distant glowing orbs, their dark matter halos just barely distinguishable from the background at a distance of 4.2 light-years. Other nearby stars like Barnard's Star, Wolf 315 and Sirius would create their own distant glows, each one revealing its mass through the intensity of its dark matter concentration. The brightest stars in our normal vision wouldn't necessarily be the brightest in dark matter vision. It would depend on their mass, not their luminosity. As we contemplate this view of our solar system bathed in dark matter light, it's worth reflecting on how different it is from the view we're familiar with. No blue Earth, no red Mars, no golden Saturn with its rings, no brilliant sun flooding everything with light. Instead, we have this patient, golden glow, these moving concentrations of light that reveal mass and gravity but nothing else. It's a simpler view in some ways, showing only one aspect of reality, but it's also profound because it reveals the invisible framework that holds everything together. The solar system in dark matter light is like seeing the skeleton of reality, the bare bones of gravity and mass without the flesh of electromagnetic phenomena. It shows us that our cosmic neighbourhood is not just the visible planets and moons we know, but also this vast invisible sea of dark matter through which everything moves. It reminds us that most of the universe is hidden from our eyes, that what we see is just a tiny fraction of what's actually there. We drift farther out now, beyond the gentle confines of our solar system's dark matter halo, out into the vast spaces between stars where the golden glow dims but never quite disappears. As we accelerate our imagination to cover impossible distances, moving at the speed of thought rather than the speed of light, the sun's dark matter concentration shrinks behind us, becoming just another point of light among many, a single golden star in a sea of dark matter illumination. We're entering the realm of the galaxy now, that vast collection of hundreds of billions of stars that we call the Milky Way, though in our dark matter vision, it appears as something entirely different from the familiar spiral of stars we know from photographs. The first thing you notice as you pull back to galactic scales is that the dark matter doesn't follow the same distribution as the visible stars. In our normal universe, the Milky Way appears as a flat disk with spiral arms, a central bulge, and a sparse halo of globular clusters. But in dark matter vision, the galaxy is more like a vast, roughly spherical cloud of golden light, extending far beyond the visible disk of stars. This is the dark matter halo of the Milky Way, and it's enormous, perhaps 600,000 light-years across, dwarfing the 100,000 light-year diameter of the stellar disk. The dark matter halo isn't uniform or featureless. It has structure, beautiful and complex structure that astronomers have only recently begun to map through careful observations of stellar motions and gravitational lensing. Near the center of the galaxy, the dark matter glow intensifies, not as dramatically as you might expect, but noticeably, creating a bright core that roughly coincides with the galactic center where our invisible supermassive black hole, Sagittarius A, lurks unseen. The black hole itself, despite its enormous mass of 4 million suns, is too small to create a distinct feature in the dark matter glow at this scale. It's lost in the general concentration of both dark and normal matter at the galaxy's heart. Moving outward from the center, the dark matter glow decreases, but not smoothly. There are streams and shells, structures left behind by smaller galaxies that the Milky Way has consumed over billions of years. Each merger, each galactic cannibalization event, has left its mark in the dark matter distribution, like growth rings in a cosmic tree. These features are invisible in normal light, hidden by the bright stars and gas of the galaxy, but in dark matter vision they're revealed as frozen rivers of light, stellar streams stripped of their visible stars but still glowing with the dark matter that once bound them together. The Sagittarius dwarf spheroidal galaxy, currently being torn apart by the Milky Way's gravity, creates a spectacular stream of dark matter that wraps around our galaxy multiple times. In our thought experiment, this stream would be visible as a golden ribbon, brighter than the background halo, spiraling through space in a complex three-dimensional pattern. It's like watching a galaxy die in slow motion, its dark matter gradually being absorbed into the Milky Way's halo, adding to our galaxy's mass and complexity. The large and small Magellanic Clouds, our galaxy's most prominent satellite galaxies, appear as distinct concentrations of dark matter light, orbiting through the Milky Way's halo like cosmic fireflies. They're not just simple points of light, but complex structures in their own right, with their own dark matter halos that interact with the Milky Ways in intricate ways. Between them and our galaxy stretches the Magellanic Stream, a vast river of gas in the normal matter universe that's invisible to our dark matter eyes. But the dark matter that accompanies this stream creates its own subtle glow, a bridge of light connecting the three galaxies. As we continue to pull back, rising above the plane of the Milky Way's disk, we can see the overall shape of our galaxy's dark matter halo. It's not perfectly spherical but slightly flattened, like an oblate spheroid, and it's not centered exactly on the visible galaxy. The dark matter halo is tilted with respect to the stellar disk, a misalignment that tells us something about the galaxy's tumultuous history of mergers and interactions. The halo also has a wake, a trail of enhanced dark matter density created by our galaxy's motion through the intergalactic medium, like the wake of a ship, but on a scale of hundreds of thousands of light years. Looking toward the Andromeda Galaxy, our nearest large galactic neighbour at 2.5 million light-years away, we see another vast concentration of dark matter light, even larger than our own. Andromeda's dark matter halo extends toward us, and our halo extends toward it, and somewhere in the middle, about halfway between the two galaxies, the halos touch. We're already interacting gravitationally with Andromeda, our dark matter halos overlapping, even though the visible galaxies won't collide for another 4.5 billion years. In dark matter vision, we can see that the collision has, in a sense, already begun. The local group, our small cluster of galaxies that includes the Milky Way, Andromeda, and about 80 smaller galaxies, appears in dark matter vision as a connected structure, a web of golden light with bright nodes where the galaxies sit and dimmer filaments connecting them. Each dwarf galaxy adds its own small contribution to the glow, and the whole system is bound together by the collective gravity of all its dark matter. The local group itself is moving through space, falling toward the Virgo cluster, creating its own wake in the cosmic dark matter distribution. As we pull back even further, to distances of tens of millions of light years, we begin to see the cosmic web itself, that largest structure in the universe. Galaxies aren't randomly distributed through space. They're organized into clusters and superclusters, connected by vast filaments of dark matter with enormous voids between them. In our dark matter vision, this structure is spectacular, a three-dimensional spiderweb of golden light stretching as far as we can see. The filaments glow with the combined light of dark matter and the galaxies embedded within them, while the voids are dimmer, though never completely dark. The Virgo cluster, the nearest large cluster to us at about 54 million light-years away, appears as an intense concentration of dark matter light, thousands of galaxies bound together by their collective gravity. The cluster is so massive that it's pulling the entire local group toward it at about 600 kilometers per second. In dark matter vision, we can see the gravitational streams connecting us to Virgo, rivers of dark matter flowing along the gravitational gradient, carrying smaller galaxies and galaxy groups toward the cluster's massive gravitational well. But Virgo itself is moving, pulled by even larger structures. The Great Attractor, a gravitational anomaly located about 250 million light-years away, influences the motion of thousands of galaxies, including our own. In normal vision, the Great Attractor is mostly hidden behind the plane of the Milky Way, obscured by dust and stars. But in dark matter vision, its presence would be obvious, a brilliant concentration of golden light marking one of the largest accumulations of mass in our cosmic neighbourhood. It's not a single object, but a confluence of several galaxy clusters, their combined dark matter creating a gravitational well that affects everything within hundreds of millions of light-years. The Shapley supercluster, even more massive than the Great Attractor and located about 650 million light-years away, would be visible as an even brighter concentration on the cosmic dark matter horizon. It's one of the most massive structures in the observable universe, containing thousands of galaxies and vast amounts of dark matter. In our imagined vision, it would appear as a golden beacon, a cosmic lighthouse whose gravitational influence extends across billions of light-years. Between these massive concentrations stretch the filaments of the cosmic web, rivers of dark matter that connect clusters and superclusters across the universe. These filaments aren't empty. They contain galaxies strung along them like pearls on a string, each one glowing with its own dark matter halo. The filaments themselves glow with a diffuse light, dark matter that's flowing along these cosmic highways, falling toward the clusters at the nodes where filaments meet. It's a dynamic structure, constantly evolving as gravity pulls matter along the filaments toward the densest regions. The voids between filaments are the darkest regions in our dark matter vision, but even they aren't completely dark. A faint, extremely diffuse glow fills even these emptiest regions of space, the background dark matter that permeates the entire universe. These voids aren't truly empty. They contain some galaxies, usually small, isolated ones, each surrounded by its own dark matter halo. But the density is so low that the dark matter glow is barely perceptible, like looking at the faintest possible candlelight from miles away. As we contemplate this vast structure, it's worth considering what we're really seeing. Each point of light, each glowing node in this cosmic web, represents billions or trillions of stars, entire galaxies with their own histories, their own planetary systems, perhaps their own life forms wondering about the nature of the universe. But in dark matter vision, all that complexity is reduced to simple points and clouds of light, revealing only the gravitational skeleton that holds everything together. It's humbling to realize that all of human history, all of Earth's history, all of our solar system's history has taken place within a tiny region of one small galaxy, in one filament of this vast web. The cosmic web isn't static. It's evolving, growing, changing over cosmic time. Galaxies move along the filaments flowing toward the clusters. Clusters themselves move and merge, creating ever larger structures. The voids expand as matter is pulled out of them toward the filaments and nodes. This evolution is slow by human standards, taking billions of years to produce noticeable changes, but it's relentless. The universe is organizing itself, gravity pulling matter into ever denser concentrations, creating structure from what was once nearly uniform. In the early universe, just a few 100,000 years after the Big Bang, the dark matter distribution was almost perfectly smooth, with only tiny fluctuations, ripples in the density that were the seeds of all future structure. Over billions of years, gravity amplified these fluctuations, pulling matter into the denser regions, creating the first dark matter halos, the gravitational wells that would eventually host the first galaxies. The cosmic web we see today in our dark matter vision is the result of 13.8 billion years of gravitational evolution, the end product of those tiny initial fluctuations growing under the relentless pull of gravity. We can see echoes of this history in the cosmic microwave background, that faint glow of radiation from the early universe that fills all of space, though the CMB itself is electromagnetic radiation and thus invisible in our dark matter vision. The fluctuations in the CMB correspond to fluctuations in the dark matter, distribution from that early time. The hotspots in the CMB mark places where dark matter was slightly denser, the seeds of future clusters. The cold spots mark places where it was slightly less dense, the future voids. The pattern we see in the CMB at a time 380,000 years after the Big Bang is the blueprint for the cosmic web we see today. Dark matter halos formed first, before galaxies, before stars, before any of the normal matter structures we're familiar with. In the early universe, dark matter began to collapse under its own gravity, while normal matter was still too hot, too energetic to collapse. The dark matter created gravitational wells, invisible pits in space-time, and when normal matter finally cooled enough to collapse, it fell into these pre-existing wells. Galaxies formed inside dark matter halos, stars formed inside galaxies, planets formed around stars, and eventually, at least in one place we know of, life emerged to wonder about it all. This hierarchy of structure, from planets to stars to galaxies to clusters to the cosmic web itself, is fundamentally shaped by dark matter. Without dark matter, galaxies would fly apart, unable to hold themselves together with the gravity of normal matter alone. Without dark matter, the cosmic web wouldn't exist. Galaxies would be more uniformly distributed through space. Without dark matter, the universe would be a very different place. Perhaps one where structures like galaxies and stars couldn't form at all, where the normal matter would remain a thin, cooling gas expanding forever into the darkness. The cosmic web also reveals something profound about the nature of space itself. What we think of as empty space, the vast voids between galaxies, isn't really empty. It's filled with dark matter, with dark energy, with quantum fields, with virtual particles popping in and out of existence. In our dark matter vision, we see that space itself has structure, has patterns, has a kind of architecture that exists independent of the normal matter we're familiar with. The cosmic web is like seeing the bones of space itself, the underlying structure that normal matter decorates but doesn't define. As we look at larger and larger scales, encompassing billions of light years, the cosmic web begins to look almost uniform again. The individual filaments and voids blur together into a kind of cosmic foam, a frothy structure that fills the observable universe. At the larger scales, the universe is remarkably uniform, the same in all directions, with no preferred center or edge. This uniformity, this isotropy and homogeneity, is one of the fundamental observations that underlies our modern cosmological models. In dark matter vision, we see this uniformity directly. the golden glow averaging out to the same intensity in all directions at the larger scales. But there are limits to what we can see, even with our imaginary dark matter eyes. The observable universe has a boundary, not a physical edge, but a horizon beyond which light hasn't had time to reach us since the Big Bang. This horizon is about 46 billion light-years away in every direction, defining a sphere centered on Earth that contains everything we can possibly observe. Beyond this horizon, there's presumably more universe, more cosmic web, more dark matter, but we can never see it, never know about it directly. It's causally disconnected from us, forever beyond our reach. In our dark matter vision, this cosmic horizon might appear as a gradual fading of the golden glow, not because the dark matter ends there, but because we're seeing it as it was longer and longer ago, eventually reaching back to a time before structures formed, before the cosmic web existed, when the dark matter was still nearly uniformly distributed. The most distant dark matter we can see is from when the universe was young, hot and smooth, before gravity had time to work its structure-building magic. The cosmic web in dark matter light also reveals the presence of dark energy, that mysterious force that's causing the expansion of the universe to accelerate. Dark energy makes up about 68% of the universe's energy density, even more than dark matter's 27%, leaving normal matter as just 5% of the cosmic pie. Dark energy acts like anti-gravity, pushing things apart rather than pulling them together, and its effects are visible in the cosmic web. The voids are expanding faster than they would from the expansion of space alone, pushed outward by dark energy. The filaments are being stretched, pulled thinner as dark energy drives the accelerating expansion. In our imagined dark matter vision, we might see this as a subtle reddening of the most distant dark matter light, a cosmic redshift caused by the expansion of space itself. The farther away we look, the redder the glow becomes, until at the cosmic horizon it fades into an infrared invisible, even to our dark matter eyes. This redshift tells us that the universe is expanding, that the cosmic web is growing, that the distances between clusters are increasing over time. It's a dynamic, evolving structure, not a static sculpture, but a living, breathing entity that changes over cosmic time. After wandering through this imagined glowing universe, let us now turn gently toward what scientists have actually discovered about dark matter, the real observations and measurements that led us to understand that most of the universe is invisible. The evidence doesn't come as dramatic revelations or sudden discoveries, but rather as quiet accumulations of observations that didn't quite make sense, small discrepancies that pointed towards something profound. Scientists have found these clues not by seeing dark matter directly, which remains impossible with our current technology, but by carefully watching how normal matter behaves when dark matter must be present, like detectives inferring the presence of an invisible person by watching how visible objects move and respond. The story begins in the 1930s with an astronomer named Fritz Zwicky, who was studying a cluster of galaxies called the Coma Cluster, located about 320 million light-years from Earth. Zwicky was measuring how fast the galaxies in the cluster were moving, using the Doppler shift of their light to determine their velocities. What he found puzzled him deeply. The galaxies were moving so fast that they should have escaped the cluster's gravitational pull long ago, flying off into intergalactic space like sparks from a pinwheel. But there they were, still bound together after billions of years. Zwicky calculated that there must be much more mass in the cluster than what he could see in the visible galaxies, perhaps 400 times more. He called this unseen mass dunkel Materie, dark matter. And though his observations were met with skepticism at the time, he had discovered something fundamental about our universe. For decades, Zwicky's observations remained a curiosity, an unexplained anomaly that most astronomers didn't take too seriously. Perhaps he had made an error in his measurements, or perhaps there was hot gas between the galaxies that he couldn't detect with the telescopes of his time. But then, in the 1970s, astronomer Vera Rubin made observations that would change everything. Rubin was studying the rotation of spiral galaxies, measuring how fast stars orbit around galactic centers at different distances. According to Newton's laws and our understanding of gravity, stars farther from the center should orbit more slowly, just as planets farther from the Sun take longer to complete their orbits. Mercury races around the Sun while Neptune plods along slowly, and the same should be true for stars and galaxies. But that's not what Rubin found. In galaxy after galaxy, she discovered that stars far from the centre were moving just as fast as stars closer in, their velocities remaining nearly constant rather than decreasing with distance. The rotation, curves as these measurements are called, were flat rather than declining. This made no sense if the only mass in galaxies was what we could see in stars and gas. The stars at the edges of galaxies were moving so fast that they should fly off into space, just like Zwicky's galaxies should have escaped their clusters, but they didn't. They stayed in their orbits, held by the gravity of something invisible, something that extended far beyond the visible edges of galaxies. The implications of Rubin's work were profound and initially met with resistance. If her observations were correct, and they were confirmed again and again by other astronomers, then most of the mass in galaxies was invisible. Not just a little bit more, not just double or triple, but 5 or 6 times as much invisible matter as visible matter. Every spiral galaxy, including our own Milky Way, was surrounded by a vast halo of dark matter, extending far beyond the beautiful spiral arms we see in photographs. The visible galaxy, all those billions of stars that we thought defined a galaxy, turned out to be just a small luminous decoration sitting in the centre of a much larger dark matter structure. These rotation curves remain one of the strongest pieces of evidence for dark matter. Scientists have now measured them for thousands of galaxies of all types, spirals, ellipticals, dwarfs, and irregulars, and they all show the same pattern. Without dark matter, these galaxies simply wouldn't exist as we see them. They would either fly apart or collapse inward, unable to maintain the stable rotation we observe. The dark matter acts like an invisible scaffolding, providing the extra gravity needed to hold galaxies together while remaining completely invisible to our telescopes. Another line of evidence comes from gravitational lensing, Einstein's prediction that massive objects bend light passing near them. When light from a distant galaxy passes by a closer galaxy cluster on its way to Earth, the cluster's gravity bends the light, creating distorted, magnified, or multiple images of the background galaxy. It's like looking through a cosmic magnifying glass, with gravity playing the role of the lens. By carefully analysing these distorted images, astronomers can map the distribution of mass in the lensing cluster, including both visible and dark matter, and what they find is that most of the mass is dark, invisible, detectable only through its gravitational effects on light. The Bullet cluster, located about 3.7 billion light-years away, provides one of the most dramatic demonstrations of dark matter's existence. This system consists of 2 galaxy clusters that collided about 150 million years ago, passing through each other like 2 swarms of bees. During the collision, the hot gas between galaxies in each cluster, which makes up most of the normal matter, collided and slowed down, heating up to millions of degrees and emitting X-rays that we can detect with space telescopes, but the galaxies themselves, being mostly empty space, passed through without colliding, and so did the dark matter, which doesn't interact with anything except through gravity. When astronomers mapped the mass distribution of the Bullet cluster, using gravitational lensing, they found something remarkable. Most of the mass was not where the hot gas was, not where most of the normal matter had ended up after the collision. Instead, the mass was in 2 separate clumps that had passed through each other, aligned with the galaxies rather than the gas. This separation of normal matter and gravitational mass is nearly impossible to explain without dark matter. The dark matter halos of the 2 clusters had passed right through each other, while the normal matter gas had collided and remained in the middle. It's like seeing 2 ghosts walk through a wall while their clothes get caught on it. A clear separation of the visible and invisible components. The cosmic microwave background radiation, that faint afterglow of the Big Bang that fills all of space, provides another window into dark matter's effects. This radiation carries an imprint of the universe, as it was 380,000 years after the Big Bang, when the first atoms formed and light could finally travel freely through space. The tiny temperature fluctuations in the CMB, variations of just a few parts in 100,000, tell us about the distribution of matter in the early universe. The pattern of these fluctuations, their statistical properties, the sizes of hot and cold spots, all of these depend on how much dark matter was present and how it behaved. Scientists have measured these patterns with exquisite precision, using satellites like WMAP and Planck, and the results clearly show that dark matter makes up about 27% of the universe's energy density, with normal matter contributing just 5%. The CMB fluctuations also tell us that dark matter is cold, meaning it was moving slowly compared to the speed of light when structures began to form, and that it's collisionless, meaning dark matter particles rarely if ever collide with each other or with normal matter. These properties are encoded in the statistics of the CMB fluctuations, a cosmic fingerprint that reveals the nature of matter we can't see. Computer simulations provide another way to test our understanding of dark matter. Scientists can program the laws of gravity into powerful supercomputers, add the measured amounts of dark and normal matter, set the initial conditions based on the CMB observations, and then let the simulation run, watching billions of years of cosmic evolution unfold in a matter of days or weeks. These simulations show that dark matter is essential for creating the cosmic web we observe. Without it, structures don't form correctly, galaxies don't develop, clusters don't assemble, and the large-scale structure looks nothing like what we see in the real universe. The Millennium Simulation, one of the largest and most detailed of these computer experiments, followed the gravitational interactions of over 10 billion dark matter particles over 13 billion years of cosmic time. The results were remarkably similar to the real universe, producing a cosmic web with the same statistical properties, the same distribution of cluster sizes, the same correlation functions as we observe. This agreement between simulation and observation gives us confidence that our understanding of dark matter, while incomplete, is fundamentally correct. But what exactly is dark matter made of? This remains one of the greatest mysteries in physics. We know what it's not. It's not normal atoms, not protons and neutrons and electrons, not any of the particles that make up the matter we're familiar with. We know some of its properties. It's cold, collisionless, stable over billions of years, and interacts primarily or only through gravity. But we don't know what it is, what particles compose it, what fundamental physics describes it. Scientists have proposed many candidates for dark matter particles. WIMPs, or weakly interacting massive particles, were long the favoured candidate. These hypothetical particles would be much heavier than protons, but would interact with normal matter only through gravity and possibly the weak nuclear force, making them nearly impossible to detect. Experiments deep underground, shielded from cosmic rays and other interference, have been searching for WIMPs for decades, waiting for the rare event when a dark matter particle might collide with an atomic nucleus and produce a tiny but detectable signal. So far, despite increasingly sensitive detectors, no confirmed detection has been made. Axions are another candidate, extremely light particles that were originally proposed to solve a problem in quantum chromodynamics, but could also make up dark matter. If axions exist, billions of them would be passing through every cubic centimetre of space every second, but their interactions with normal matter would be even weaker than WIMPs. Experiments are searching for axions by looking for their conversion to photons in strong magnetic fields, but again, no confirmed detection yet. Sterile neutrinos, primordial black holes, superfluid dark matter, self-interacting dark matter, the list of candidates goes on, each with its own theoretical motivation and experimental search strategy. Some scientists have even proposed that dark matter isn't a particle at all, but a modification of gravity itself, that our laws of gravity need adjustment on galactic and cosmic scales. These modified gravity theories, like MOND, modified Newtonian dynamics, can explain some observations like galaxy rotation curves, but struggle with others, like the bullet cluster and the CMB patterns. The Large Hadron Collider, the world's most powerful particle accelerator, has been searching for signs of dark matter production in high-energy collisions. If dark matter particles can be created in these collisions, they would escape the detector without interacting, carrying away energy and momentum, leaving a telltale signature of missing energy. But so far, no such signatures have been definitively observed, placing constraints on what dark matter could be, but not revealing its nature. Direct detection experiments continue to become more sensitive, using tanks of liquid xenon, crystals of germanium, or other materials, waiting deep underground for the whisper of a dark matter interaction. The xenon, Lux, Pandix and other experiments have pushed the sensitivity to incredible levels, able to detect the energy from a single electron being knocked out of place. Yet dark matter remains elusive, either interacting even more weakly than we thought, or perhaps not interacting at all except through gravity. Indirect detection searches look for the products of dark matter, annihilation or decay. If dark matter particles can annihilate when they meet, they might produce gamma rays, cosmic rays, or neutrinos that we could detect. The Fermi Gamma Ray Space Telescope, the Alpha Magnetic Spectrometer on the International Space Station, and the Ice Cube Neutrino Observatory at the South Pole all search for these signals. There have been some intriguing hints: excess gamma rays from the galactic centre, an unexpected positron fraction in cosmic rays, but nothing conclusive enough to claim discovery. The fact that we haven't detected dark matter particles directly, despite decades of searching with ever more sensitive instruments, tells us something important. Dark matter is even more elusive than we initially thought, its interactions with normal matter even weaker, its nature even more foreign to our everyday experience. It's humbling to realise that after all our technological progress, after building detectors that can sense single photons and individual atoms, we still can't directly detect the substance that makes up most of the matter in the universe. Yet the gravitational evidence remains overwhelming. Every new observation, every more precise measurement confirms that dark matter is there. The way galaxies rotate, the way clusters bend light, the patterns in the cosmic microwave background, the structure of the cosmic web, all of these independent lines of evidence point to the same conclusion. Most of the matter in the universe is invisible to us, detectable only through its gravity. It's not a mistake, not an error in our measurements, not a misunderstanding of the data. Dark matter is real, even if we don't yet know what it is. This situation, knowing something exists but not knowing what it is not unprecedented in science. 19th century astronomers knew that Uranus's orbit was being perturbed by something, and they correctly predicted the existence and location of Neptune before it was directly observed. Early 20th century physicists knew that something was carrying energy away from beta decay, and they correctly proposed the existence of neutrinos decades before they were detected. Perhaps we're in a similar situation with dark matter, knowing it's there, knowing some of its properties, but not yet having the technology or insight to detect it directly. The search for dark matter has also revealed something profound about the nature of scientific inquiry. We've learned that the universe doesn't always reveal itself easily, that some of nature's secrets require patience, ingenuity, and humility to uncover. We've learned that what we can see is not all there is, that our senses and even our instruments show us only a small fraction of reality. We've learned that the universe is stranger and more mysterious than our ancestors could have imagined, filled with invisible substances and hidden structures that shape everything we see. With the gentle foundation of what is known laid before us like a map of explored territories, we move now into the softer, more speculative realm of what might be, where the boundaries of knowledge blur into imagination and possibility. Perhaps dark matter is made of unknown particles that we haven't yet imagined, particles that obey laws of physics we haven't yet discovered, existing in a realm just beyond our current understanding. Like a room we know must exist in a house, but haven't yet found the door to enter. Perhaps it is a sign that our understanding of gravity itself is not yet complete, that Einstein's beautiful theory of general relativity, as successful as it has been, is only an approximation of something deeper, something that would naturally explain what we now call dark matter without invoking new particles at all. We explore these ideas slowly, thoughtfully, like walking through different paths in a quiet, starlit garden, where each path represents a different possibility, a different way the universe might be constructed. None of these paths need to be the right one for our journey to be meaningful. The wandering itself is a kind of cosmic meditation, a gentle exercise in stretching our minds to accommodate possibilities we haven't yet fully grasped. The technical words and theories that scientists use, WIMPs and axions and modified gravity, these can blur into a pleasant background hum if you let them, like the sound of a distant waterfall that you know is there but don't need to analyse to appreciate. Let's begin with WIMPs, those weakly interacting massive particles that have captured physicists' imaginations for decades. The name itself is almost whimsical, but the idea is profound. What if dark matter consists of particles that are heavy, perhaps 100 times heavier than a proton, but that interact with normal matter only through gravity and the weak nuclear force? The weak force is one of the 4 fundamental forces of nature, responsible for certain types of radioactive decay, and it's called weak because it's much feebler than the electromagnetic force that governs chemistry and light. If dark matter particles interact, through the weak force they would pass through normal matter almost unimpeded, like neutrinos but more massive, leaving only the faintest traces of their passage. In our imagined universe where dark matter glows, WIMPs would be the individual sparkles in that golden light, each one a tiny firefly drifting through space on its own trajectory, responding only to gravity's gentle pull. They would have been created in the first fraction of a second after the Big Bang, when the universe was hot enough and dense enough for such exotic particles to form, and they would have survived until today because they're stable, having no way to decay into lighter particles. The number of WIMPs created in the early universe would have been determined by a delicate balance of physics, and remarkably, if we calculate how many would have been produced, we get approximately the right amount to account for the dark matter we observe today. This numerical coincidence, sometimes called the WIMP miracle, has made WIMPs an attractive candidate for dark matter. It seems too perfect to be mere chance, like finding that a key you've been carrying fits a lock you've just discovered. But perhaps that's just our human tendency to see patterns and meaning where none exist, or perhaps it's a genuine clue about the nature of dark matter. Scientists have built elaborate experiments to search for WIMPs, detectors buried deep underground to shield them from cosmic rays, filled with ultra-pure materials cooled to near absolute zero, waiting patiently for the rare collision between a WIMP and an atomic nucleus that would announce the presence of these elusive particles. The xenon experiment in Italy, buried under a mountain to protect it from interference, uses tons of liquid xenon as a target. When a particle interacts with a xenon nucleus, it produces a tiny flash of light and releases electrons, both of which can be detected with exquisite sensitivity. The detector is so sensitive that it can see the recoil of a single atom, like detecting the movement of a bowling ball when a feather brushes against it. Yet despite years of observation, no clear WIMP signal has emerged, only better and better limits on how weakly these particles must interact if they exist at all. Perhaps WIMPs are even more elusive than we thought, or perhaps they don't exist at all. This brings us to another possibility: axions, particles so light and so weakly interacting that billions of them could be passing through your body right now without any effect whatsoever. Axions were originally proposed to solve a completely different problem in physics, the strong CP problem in quantum chromodynamics, but scientists realized that if axions exist with the right properties, they could also be dark matter. Unlike WIMPs, which would be heavy and slow-moving, axions would be incredibly light, perhaps a billionth the mass of an electron, but there would be so many of them that they could still account for dark matter's gravitational effects. If dark matter is made of axions, our glowing dark matter universe would look different at the smallest scales. Instead of individual particles moving on independent trajectories, axions would behave more like a fluid, or even a wave, a cosmic ocean of oscillating quantum fields that fills all of space. In the centers of galaxies where the density is highest, axions might form a Bose-Einstein condensate, a state of matter where quantum effects become visible on macroscopic scales. The dark matter glow in our imagined universe might shimmer and pulse with quantum interference patterns, like the surface of a soap bubble, but on galactic scales. The Axion Dark Matter Experiment, or ADMX, searches for these ghostly particles using a different approach than WIMP detectors. It uses strong magnetic fields and microwave cavities to try to convert axions into photons, turning dark matter into light that we can detect. The experiment must be tuned to exactly the right frequency, like tuning a radio to find a distant station, slowly scanning through possibilities, listening for the faint signal that would announce the discovery of axions. So far, silence, but the search continues, gradually excluding more and more of the possible parameter space where axions could hide. Then there are sterile neutrinos, hypothetical cousins of the regular neutrinos we know exist. Regular neutrinos are already ghostly, able to pass through light years of lead without interacting, but they're too light and too fast-moving to be dark matter. Sterile neutrinos would be heavier and wouldn't interact through any of the known forces except gravity, making them even more elusive than regular neutrinos. They're called sterile because they would be completely inert to all forces except gravity, unable to participate in any of the interactions that make normal matter interesting and complex. Some scientists have proposed that dark matter might not be a single type of particle, but a whole dark sector of physics, with multiple types of dark matter particles that interact with each other through new dark forces that we can't detect. Just as normal matter includes electrons, protons, neutrons, and all the other particles of the Standard Model, dark matter might have its own rich structure that we're completely unaware of. There could be dark atoms, dark chemistry, even dark stars that shine with dark light invisible to us. In our imagined universe where dark matter glows, this dark sector might create complex patterns and structures beyond the simple halos and streams we've been envisioning. But perhaps we're thinking about this all wrong. Perhaps dark matter doesn't exist at all, and what we're seeing is a sign that our theory of gravity needs modification. This idea, called modified Newtonian dynamics or MOND, suggests that gravity behaves differently at very low accelerations, like those found at the edges of galaxies. In regions where gravity is extremely weak, perhaps it doesn't follow the inverse square law that Newton discovered and Einstein refined. Perhaps it falls off more slowly with distance, providing the extra pull needed to explain galaxy rotation curves without invoking dark matter. MOND can successfully explain many observations, particularly the rotation curves of galaxies, with remarkable precision. It even makes predictions that have been verified, like the relationship between a galaxy's mass and its rotation speed. But MOND struggles with other observations like the bullet cluster, where we see a clear separation between normal matter and the source of gravity, or the patterns in the cosmic microwave background that seem to require dark matter to explain. Various relativistic versions of MOND have been proposed to address these issues, but none have been completely successful. Another possibility is that dark matter is made of primordial black holes, tiny black holes formed in the extreme conditions of the early universe rather than from collapsing stars. These black holes could have a wide range of masses, from less than an asteroid to more than a star, and they would be completely dark, detectable only through their gravity. If dark matter is primordial black holes, our glowing universe would look different again, with point-like sources of intense gravitational fields rather than smoothly distributed particle clouds. Gravitational microlensing surveys have placed constraints on how much dark matter could be in the form of black holes, but some mass ranges remain possible. There's even the possibility that dark matter is something we haven't thought of yet, something that would seem obvious in hindsight, but that we can't imagine with our current knowledge. History is full of such examples. Before the discovery of atoms, no one could have imagined that matter was mostly empty space. Before quantum mechanics, no one could have conceived that particles could be in multiple places at once, or that observing something could change its properties. Perhaps dark matter will require a similar conceptual leap, a new way of thinking about matter and space and gravity that we haven't yet developed. The search for dark matter has led to the development of incredibly sensitive technologies and detection methods. We've built detectors that can sense the energy from a single photon, measure the recoil of a single atom, detect temperature changes of a millionth of a degree. We've sent telescopes to space to look for gamma rays from dark matter annihilation, buried detectors miles underground to shield them from cosmic rays, and cooled experiments to within a fraction of a degree of absolute zero to reduce thermal noise. Each improvement in sensitivity, each new technique, opens a new window to search for dark matter. But so far, all windows have shown us only darkness. Perhaps dark matter interacts so weakly that we'll never detect it directly, only infer its presence through gravity as we do now. This wouldn't be unprecedented. We've never directly detected gravitons, the hypothetical particles that carry the gravitational force, and we may never be able to. Some aspects of nature might be forever beyond our direct observation, knowable only through their effects on things we can see. This doesn't make them less real, just more mysterious, more humble reminders of the limits of human perception and technology. The possibility that we might never directly detect dark matter particles has led some scientists to focus on understanding its gravitational effects in ever greater detail. By mapping the distribution of dark matter through gravitational lensing, studying the motions of stars and galaxies with unprecedented precision, and simulating the formation of cosmic structure with ever more powerful computers, we can learn about dark matter's properties even if we can't capture it in our detectors. It's like studying the wind by watching how it moves leaves and branches, inferring the properties of something invisible from its visible effects. Future telescopes and surveys will map the distribution of dark matter across the universe with extraordinary precision. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will photograph the entire visible sky every few nights, tracking how galaxies are distorted by gravitational lensing to create the most detailed map of dark matter ever made. The Euclid Space Telescope will survey billions of galaxies, measuring their shapes and distances to trace the cosmic web of dark matter across billions of light years. The Nancy Grace Roman Space Telescope will use gravitational microlensing to search for dark matter in the form of black holes or other compact objects. These observations might reveal surprises about dark matter that we haven't anticipated. Perhaps dark matter isn't distributed exactly as our simulations predict. Perhaps there are features in its distribution that hint at new physics. Perhaps the way dark matter clusters on different scales will tell us something fundamental about its nature. Each observation is a piece of the puzzle, and even though we don't know what the final picture will look like, we keep collecting pieces, trusting that eventually a pattern will emerge. In our imagined universe where dark matter glows, all these different possibilities would manifest as different patterns of light. WIMP dark matter might create a smooth, diffuse glow with subtle streams and structures. Axion dark matter might shimmer with quantum interference patterns. Primordial black holes would appear as countless point sources of intense gravitational light. Modified gravity wouldn't produce any glow at all, since there would be no dark matter, just different behaviour of space-time itself. Each possibility paints a different picture of the invisible universe, and perhaps one day we'll know which picture is correct, or perhaps the truth is stranger than any of these possibilities. Now we return to ourselves, to humanity, and wonder gently who we might be in such a universe, where the invisible majority makes itself known through patient golden light. If dark matter glowed in the night, if we could see those vast halos and streams and cosmic webs with our naked eyes, how different would human civilization have developed? How would our stories, our philosophies, our understanding of our place in the cosmos have evolved if we had always known that we were made of the rare exotic matter, the small exception rather than the rule? Imagine ancient humans, perhaps 100,000 years ago, looking up at night sky not punctuated by points of starlight, but glowing with the soft, continuous radiance of dark matter structures. The Milky Way wouldn't appear as a river of stars, but as a vast golden aurora, a three-dimensional halo of light extending far beyond what we now call the galactic disk. Early humans might have seen themselves as living within a cosmic cocoon of light, surrounded and protected by this gentle glow that never changed with the seasons, never rose or set, but simply existed, patient and eternal. The mythologies that grew from such a sky would be profoundly different from the ones we know. Instead of constellations made of stars, stories of heroes and monsters drawn with points of light, there might be tales of the great golden rivers that flow between the bright mountains of the sky, the vast breathing patterns of cosmic light that pulse so slowly that only the shamans who watch for generations can perceive their rhythm. The dark matter streams might be seen as the paths of ancestors, the roads that souls travel after death, visible proof of a continuity that transcends individual existence. Agricultural societies might have developed different calendars, not based on the movement of stars and planets which would be invisible, but on subtle variations in the dark matter glow. Perhaps they would notice the monthly brightening and dimming caused by the moon's invisible orbit, or the yearly cycle as Earth moves closer to and farther from the sun's dark matter concentration. These cycles would be much subtler than the dramatic seasonal changes we use, requiring careful observation and record keeping, possibly leading to an earlier development of precise measurement and mathematical thinking. Navigation would have evolved along entirely different lines. Without stars to guide them, sailors and travellers would need to read the subtle patterns in the dark matter glow. Mountain ranges would appear as glowing beacons, valleys as darker channels, and the gravitational effects of invisible continents and ocean basins would create patterns in the light that skilled navigators could learn to read. Perhaps they would develop instruments to measure the intensity and direction of the dark matter glow, cosmic sextants that measure gravitational rather than celestial positions. The development of science might have taken a different path as well. The constant presence of the dark matter glow would make it obvious from the beginning that there's more to the universe than what we can touch and feel. The invisible nature of normal matter in this reversed universe might have led to an earlier understanding that our senses don't reveal everything, that reality extends beyond what we can directly perceive. Perhaps this would have made humanity more humble, more aware of our limitations, more open to possibilities beyond our immediate experience. In our imagined world, cities would be designed differently. Without the need for artificial lighting to see at night, Since the dark matter glow would provide constant illumination, architecture might focus more on controlling and shaping this natural light. Buildings might be designed to concentrate or diffuse the dark matter glow, creating spaces of different luminous intensity for different purposes. Sacred spaces might be built in locations where the dark matter glow is particularly intense, where invisible mountains or dense geological formations create natural cathedrals of light. Art would take on completely different forms. Visual art couldn't depict objects or people since they would be invisible, but it might focus on the patterns and flows of dark matter light. Artists might create gravitational sculptures, arrangements of invisible mass that produce beautiful patterns in the dark matter glow. Music might be more important, or perhaps art forms we can't even imagine. Ways of manipulating gravity or dark matter itself to create aesthetic experiences. The whole concept of beauty would be different, based on the subtle variations of golden light rather than colour and form. Human relationships and society would be profoundly affected by universal invisibility. Privacy as we know it wouldn't exist, or rather, it would be absolute since no one could see anyone else. Communication would rely entirely on sound, touch, and perhaps smell. We might develop much more sophisticated vocal communications, languages that convey through tone and timbre what we normally convey through facial expressions and body language. Or perhaps we would develop technologies early on to make ourselves visible, some way to interact with dark matter to create visible markers of our presence. The discovery that we're made of rare, exotic matter in a universe dominated by something else entirely would shape philosophy and religion in profound ways. Instead of seeing ourselves as central to creation, made of the same stuff as stars, we would know from the beginning that we're anomalies, tiny exceptions in a cosmos made mostly of something else. This might lead to a more humble view of humanity's place in the universe, or perhaps to a sense of being special, chosen, the only known arrangement of matter that can think and wonder about the golden glow that surrounds us. Modern science, in this reversed universe, would focus on understanding normal matter as the mystery, the strange 5% of the universe that behaves so differently from everything else. Scientists would wonder why normal matter interacts electromagnetically, why it forms atoms and molecules and chemistry, why it can create the complexity of life when dark matter cannot. The discovery of electromagnetism would be as revolutionary as the discovery of dark matter has been in our world, revealing a hidden force that explains the behavior of the mysterious invisible matter that makes up our bodies. The environmental movement might take on different dimensions. Without visible nature, without blue skies and green forests and sparkling waters to inspire protection, the motivation for conservation would be different. Perhaps it would focus on preserving the gravitational patterns that dark matter reveals, protecting the invisible mountains and valleys that create the landscape of light we navigate by. Or perhaps the very invisibility of environmental damage would make it harder to recognize and address, until it affects the dark matter glow in noticeable ways. Space exploration would be driven by different motivations. Without visible stars and planets to inspire us, the desire to explore might come from wanting to understand the structures we see in the dark matter glow. We would know from the beginning that we're embedded in a vast cosmic web, that streams and filaments of dark matter connect us to distant parts of the universe. The first astronauts wouldn't see the Earth as a blue marble, but as a golden orb, a concentration of light in the darkness, and this might give us a different perspective on our home's fragility and preciousness. The search for extraterrestrial life would focus on different signatures. Instead of looking for radio signals or atmospheric biosignatures, we might search for anomalies in the dark matter distribution that could indicate the presence of large-scale civilizations. If advanced aliens could manipulate dark matter, they might create visible structures or signals in the golden glow, cosmic lighthouses that announce their presence across the universe. SETI researchers would study the cosmic web for patterns that seem too regular, too intentional to be natural. Psychology and neuroscience would grapple with different questions about consciousness and perception. In a world where everyone is invisible, the concept of self-image would be radically different. Body dysmorphia couldn't exist in the same way, but perhaps there would be other disorders related to one's gravitational presence or the inability to see oneself in the dark matter glow. The mirror stage of child development that psychologists talk about, where children recognize themselves in mirrors, would be impossible, leading to different theories about how self-awareness develops. Education would emphasize different skills. Without visible writing, Knowledge might be transmitted primarily through oral traditions, or perhaps we would develop tactile writing systems earlier, like Braille. Mathematics might be more advanced since it doesn't rely on visibility, while visual arts and literature as we know them might not exist at all. Children would learn to navigate by reading the dark matter glow, to recognize places by their gravitational signatures rather than their appearance, to understand their world through a completely different sensory framework. Philosophy would wrestle with different fundamental questions. The mind-body problem would be even more acute when bodies are invisible. How do you understand the relationship between consciousness and physical form when you can't see physical forms? The question of other minds would be more pressing when you can't see others at all, only hear their voices and feel their touch. Solipsism, the idea that only one's own mind is sure to exist, might be harder to refute when the external world is largely invisible. The concept of death would carry different meanings. Without visible bodies, death might be understood differently, perhaps as a cessation of sound and movement rather than a visual change. Funeral rites might focus on the gravitational absence left behind, the subtle dimming of the dark matter glow where a person's mass once contributed its tiny share. Or perhaps the invisibility of bodies would make death seem less final, easier to deny or mythologize. Love and attraction would operate through different channels. Without visual beauty to spark initial attraction, relationships might form based more on voice, scent, touch, and personality from the start. The concept of love at first sight would be impossible, replaced perhaps by love at first sound or love at first touch. This might lead to deeper, more substantive connections, or it might make forming relationships more difficult without the visual cues we rely on. Technology would develop along different trajectories. Without the need for artificial lighting, enormous amounts of energy that our civilization devotes to illumination would be directed elsewhere. Perhaps we would develop gravity manipulation technology, ways to shape the dark matter, glow for communication, or art. Computing might be based on gravitational rather than the electronic principles. The internet, if it developed at all, might be a network of gravitational signals rather than electromagnetic ones. War and conflict would take different forms in an invisible world. Military strategy couldn't rely on visual reconnaissance or camouflage. Weapons might be designed to disrupt gravitational fields rather than destroy visible structures. The concept of territory might be based on gravitational signatures rather than visible borders. Peace might be easier to maintain when you can't see differences in appearance that often divide us, or perhaps conflict would find other reasons to flourish. As we contemplate these possibilities, we realize how profoundly our visible universe shapes everything about human existence. Our art, science, philosophy, relationships, entire civilizations are built on the foundation of electromagnetic interaction, on the fact that light bounces off normal matter and enters our eyes, creating the rich visual world we navigate. In a universe where dark matter glowed and normal matter was invisible, humanity might still exist, might still develop intelligence and civilization, but it would be an utterly alien humanity, shaped by different forces, guided by different senses, dreaming different dreams. Yet in both universes, the real one we inhabit and the imagined one we've been exploring, humans would still be seekers of truth, still be curious about the nature of reality, still wonder about their place in the cosmos. Whether we see by electromagnetic light or imaginary dark matter glow, we would still look up at the sky and ask why, how, what does it mean? The tools would be different, the path of discovery would follow different routes, but the fundamental human drive to understand, to find meaning, to connect with something larger than ourselves, that would remain. At the end of this long, slow journey through imagination and reality, through visible and invisible realms, we return once more to the simple question that began it all, that gentle wondering that invited you to see the universe differently. What if dark matter were visible and normal matter invisible? The question remains unanswered in any definitive sense, and that is perfectly, beautifully okay. Questions like these aren't meant to be solved like mathematical equations or resolved like plot points in a story. They're meant to be lived with, contemplated, allowed to slowly reshape how we understand our place in the vast, patient cosmos that surrounds us. We've wandered far in our imagination, haven't we? From your room where this journey began, where you first started to envision the walls becoming transparent and the dark matter beginning to glow, all the way out to the cosmic web spanning billions of light years, that vast golden spider's web that holds all galaxies in its patient embrace. Now, as our exploration draws to a close, let's retrace our path, but gently, dreamily, like remembering a pleasant dream as you drift towards sleep, each image softer and less defined than the last. Remember how it felt when your familiar world first began to change, when the solid walls that define your personal space became as clear as air, when your own hands became transparent, invisible, yet somehow still present, still yours. That strange sensation of being both there and not there, existing in the same space but in a different way, that was your first taste of how profoundly different reality could be with just one fundamental change. In the quiet depths of space, in the silence between stars, that transformation continues even now in your imagination, a gentle shifting between what is and what might be. The Earth beneath you, our small blue world that in this imagined universe you cannot see, revealed itself through the golden glow of dark matter pooling in its gravitational well. Not the sharp sphere we know from photographs, but a gentle concentration of light, softer at the edges, more felt than seen. You learn to navigate not by landmarks, but by the subtle variations in that glow, the brightening near invisible mountains, the dimming over invisible oceans, a completely different map of the same familiar world. And then we rose higher, didn't we? Up through the transparent atmosphere into the space between worlds, where the moon traced its path as a moving concentration of golden light, where the planets revealed themselves not through their colours or features, but through their gravitational presence alone. Jupiter, that giant among worlds, became a beacon second only to the sun, while little Mercury raced around our invisible star as a tiny spark, barely distinguishable from the background glow. The asteroid belt and Kuiper belt appeared as gentle rings of enhanced light, and far beyond, the hypothetical Oort cloud created the faintest possible sphere of illumination at the very edge of our sun's gravitational kingdom. In the silence between stars, we saw how our solar system is just one small eddy in the vast flows of dark matter that fill our galaxy. The Milky Way revealed itself not as a spiral of stars, but as the enormous halo of golden light, roughly spherical, extending far beyond anything we can see with normal eyes. Streams of dark matter from devoured galaxies spiral through this halo like frozen rivers, and our motion through this invisible sea creates a wind that blows through everything. Through you right now as you listen, billions of particles passing through your body every second without the slightest interaction. Perhaps in some other universe, some parallel reality that physicists speculate about, dark matter really does glow with that golden light we've imagined. Perhaps there are beings there who evolved to see it, who built their entire civilization around navigating and understanding those patient patterns of gravitational light. They would know nothing of stars as points of light, nothing of blue skies or green plants, or the faces of their loved ones. Their poetry would sing of the cosmic streams, their art would shape gravitational fields, their science would struggle to understand the mysterious 5% of invisible normal matter that they know must exist but cannot see. What if, just maybe, consciousness itself could arise from dark matter in that other universe? Not life as we know it, not chemistry and DNA and cells, but something else entirely, some form of organization we can't imagine that uses dark forces instead of electromagnetic ones. These dark matter beings, if they existed, might be vast, spread across light years, thinking thoughts that take millions of years to complete. Or they might be tiny, quantum entities flickering in and out of existence in the densest dark matter regions at the centers of galaxies. They might be wondering right now about us, about the strange normal matter that seems to glow with electromagnetic radiation, but doesn't respond to their dark forces. In the quiet depths of space, these possibilities multiply infinitely. Every question leads to more questions. Every answer opens new mysteries. That's the beauty of wondering about dark matter, about this invisible majority of the universe. It reminds us that what we know is always exceeded by what we don't know, that the familiar world we navigate every day is just a tiny fraction of a reality far stranger and more wonderful than our senses can perceive. Consider the possibility that this is not a limitation but a gift, that the mystery itself is what makes existence beautiful, what gives us reason to keep exploring, keep wondering, Keep reaching for understanding that always remains just beyond our grasp. The cosmic web we envisioned, that vast network of golden filaments connecting galaxy clusters across billions of light years, remains one of the most beautiful structures in our imagined universe. Even now, as you rest and listen, you're embedded in that web, sitting at one tiny point along one filament, surrounded by streams and flows of dark matter you cannot see. The Earth, the Sun, our entire galaxy, we're all nodes in this vast network, connected to everything else by invisible threads of gravity and dark matter. In the silence between stars, these connections persist, patient and eternal, whether we can see them or not. Scientists continue their quest to understand dark matter, building ever more sensitive detectors, proposing new theories, searching for signals that might reveal its nature. But perhaps the mystery is meant to last longer. Perhaps we're still in the early chapters of this story, like ancient astronomers who could see the planets but couldn't imagine they were other worlds. Future generations might look back at our current confusion about dark matter with the same gentle amusement we feel toward those who thought the Earth was the center of the universe. Or perhaps dark matter will remain forever mysterious, a fundamental reminder that the universe doesn't owe us understanding, doesn't promise that all its secrets can be unlocked. Somewhere in the cosmic darkness, right now as you drift towards sleep, dark matter is flowing through your room in invisible streams. It's passing through your body, through the Earth, through everything, following trajectories determined by the gravitational dance of galaxies. You can't feel it, can't see it, can't detect it with any sense you possess, but physics tells us it's there, patient and persistent as gravity itself. What if, just for tonight, you could feel it? Just the slightest sensation, like the gentlest breeze on a perfectly still night, like the faintest warmth from a distant fire. Let that imagined sensation carry you deeper into rest now. The questions we've explored don't need answers tonight. They don't need resolution or conclusion or any kind of closure. They can simply exist in your mind like the dark matter exists in space, invisible but present, unfelt but influential, mysterious but real. In the quiet depths of space, in the silence between stars, questions and mysteries are as natural as gravity, as fundamental as the passage of time. The universe we've imagined, where dark matter glows and normal matter is invisible, fades now back into possibility, back into the realm of what if and maybe. But something of it remains, doesn't it? A different way of thinking about the cosmos, a new appreciation for how much remains hidden, a gentle wonder at being part of something so vast and strange. You're made of the rare, exotic matter in a universe dominated by something else entirely. You're the exception, the anomaly, the 5% that somehow became conscious and started wondering about the other 95%. Every atom in your body, every particle of normal matter that makes you who you are, was forged in the hearts of stars that lived and died before our sun was born. You are stellar ash, cosmic dust that learned to think, the universe becoming aware of itself, and you exist in an ocean of dark matter, surrounded by it, moving through it, shaped by its gravity even though you cannot perceive it. You're both central and peripheral, both vitally important and cosmically insignificant, both the observer and the observed in this strange, beautiful universe we inhabit. As sleep approaches, or perhaps has already begun to claim you, let the images we've explored soften and blur. The golden glow of dark matter dims to a gentle amber, then to the faintest suggestion of light, then to nothing at all, or rather, to the nothing that's really something, the invisible presence that surrounds us always. The cosmic web relaxes its hold on your attention, the galaxies drift apart in your mind, the solar system settles into its ancient rhythms that continue whether we observe them or not. What remains is just the question, that simple, impossible question that started our journey. What if dark matter was visible and normal matter invisible? It hangs there in the darkness of your mind like a star, neither demanding an answer nor offering one, simply existing as a point of wonder in the vast space of possibilities. And that's enough. That's more than enough. That's perfect, actually, because the best questions, the ones that really matter, are the ones that don't have easy answers, the ones that invite us to wonder rather than to know. In the quiet depths of space, in the silence between stars, in the pause between one breath and the next, The universe continues its patient existence, dark matter flowing in invisible streams, normal matter glowing with electromagnetic radiation, gravity binding it all together, and patterns too complex for any human mind to fully grasp. You are part of those patterns, a tiny swirl in the cosmic currents, a brief arrangement of atoms that for this moment has the extraordinary ability to wonder about it all. Tomorrow, or whenever you wake, the familiar world will return. Walls will be solid and opaque again, your hands visible, the stars points of light in a dark sky rather than nodes in a golden web. But perhaps you'll remember something of this journey, some faint echo of what it felt like to imagine the universe differently. Perhaps you'll look at the empty space around you and remember that it's full of invisible dark matter. Perhaps you'll feel a little more connected to the cosmic web, knowing that you're part of structures that extend far beyond anything you can see. Or perhaps you'll forget it all, and that's okay too. The universe doesn't require us to remember or understand. It simply is, patient and eternal, visible and invisible, known and mysterious, waiting for us whenever we're ready to wonder about it again. The questions will still be there, as constant as dark matter itself, ready to spark new journeys of imagination whenever you need them. Let go now of any need to hold on to these ideas, any effort to remember or understand. Let them drift away like leaves on a stream, like galaxies flowing along cosmic filaments, like dark matter particles on their billion-year orbits. What matters isn't the specific details, but the feeling they've created, the sense of wonder, the peaceful recognition that we're part of something vast and mysterious and beautiful. You're a small, meaningful part of a much larger, peaceful mystery. The universe cradles you in its invisible structures, holds you with its patient gravity, includes you in its vast, slow evolution towards something we cannot imagine. In the quiet depths of space, in the silence between stars, in the gentle glow of imagined dark matter, you belong. You have always belonged. You will always belong. Sleep now, if sleep is what comes next. Or simply rest in the darkness that isn't really dark, the emptiness that isn't really empty, the silence that's full of invisible wonders. The universe continues its ancient dance, whether you watch or not. Dark matter and normal matter intertwined in patterns of such complexity and beauty that we've barely begun to glimpse them. The question that began our journey needs no answer. It can rest now too, settling into the depths of your mind like sediment in still water, like dark matter in a gravitational well, like thoughts in the moment before sleep. What if dark matter was visible and normal matter invisible? The question itself is the answer. The wondering is the destination. The journey we've taken together is the only conclusion we need. In the cosmic quiet, in the patient darkness, in the invisible embrace of dark matter that surrounds us all, rest now. Rest completely. Rest knowing that the mysteries will still be there when you return, that the universe will continue its wonders, whether you observe them or not, that being small and temporary in something vast and eternal is not a limitation, but a gift, not a source of anxiety but of profound peace. The golden glow fades completely now, the last traces of our imagined dark matter light dimming to nothing, leaving only the familiar darkness behind your closed eyelids, the comfortable darkness of approaching sleep, the darkness that isn't dark matter or normal matter, but simply rest, simply peace, simply the quiet end of one journey and the gentle promise of dreams to come.